the actual special relativistic part of the lecture series. The last couple of weeks we've been discussing how electromagnetism and electrodynamics works, and I hope that you've all seen how ridiculously easy the theory actually is in a certain sense. It might be mathematically difficult, but we found ultimately that the expressions for the scalar potential, for the vector potential, for the E field and the B field are all given by exactly the same type of differential equation. And we have written down the general solution to that thing. So that means that if somebody gives you a charge density or a current, you will be able to write down the solution immediately for every single situation. So that means that all of electrodynamics, I'm not joking here, I'm not being sarcastic or ironic, I mean that you actually solve all of electrodynamics. So the only thing that's still left for us to do is recast everything that we know into a special relativistic framework. We've been hinting towards this, that you can do this, that electrodynamics has special relativity built into it from the outset. And of course, this is how historically special relativity was found. That people had this relativistic electrodynamics, or electrodynamics as it was called back in the day. And then people, most notably Einstein, found, wait a minute, there are some symmetries built into here. You can actually change a magnetic field into an electric field and the other way around just by moving from one observer frame to the other. An example that I've already mentioned before was that, well, if you happen to be a charged particle, I now see an electric field, and I now am able to completely write down what the electric field is and the scalar potential at this particular position that I'm at. How? Well, the only thing I have to do is just identify how much charge there is here at what position. That gives me a charge density, a rho, put it into either my Maxwell equations or this general solution that we have written down, and I know exactly what my scalar potential is and my electric field at this point. So that's one setup. But here's a change. Same guy, same amount of charge, same location, it's just that I happen to be moving, and that means that with respect to me, I now not only see a charge density, I also see a current, because he's now a moving charge in my observer frame. But that means that I don't just see an electric field now in this frame, I also see a magnetic field, because there's now a current, a J, on top of the rho. And people were already aware of that apparently in electromagnetism, you can change magnetic fields into electric fields in the other way around, just by moving, just by going to another observer frame. Now, it is not obvious at all that if I then do my experiment, suppose I have this charged particle in my hand here and I see how it moves because of your presence, that standing still and doing this exercise will make this charge start moving around. Suppose your negative charge has a negative charge here, they will repel, right? Will move backwards or something like that. It is not obvious at all that if I change to this particular coordinate system with this thing in my hand, that this electron will now also move in exactly the same way. I mean, sure, there's still the electric field, there's still repulsion, but there's also now a moving charge and a current, so that means the magnetic fields also start pushing on that thing. And that it will give us the same solution, regardless of whether I was standing still or moving, is completely not obvious. So originally what people thought was this, just historically speaking, say late 19th century. The original thought that people had was, well, either this guy who's standing still with his charge in his hand is allowed to use Maxwell's equations and find some solution, and his solution happens to be correct, this is what nature does. Or the other guy who happens to be moving with respect to him is allowed to use the Maxwell equations, because that will give some other, quote unquote, will sort of give us some other experimental prediction. And it was not obvious that these predictions should give you exactly the same result. It's not obvious from the mathematics itself. And the original idea was, well, apparently one person is allowed to use the Maxwell equations and the other one simply isn't. In other words, there is a frame, an observer frame, suppose it's this guy, the guy who was standing still, who is allowed to use Maxwell's equations, but not the other guy. In other words, Maxwell's equations are not applicable in all observer frames. And does that make sense? I mean, at first that might be the case. If you change from one observer to the next, all of a sudden you introduce magnetic fields, it looks as if you will get completely different predictions. But if you have two observers with different predictions, then one of them at least must be wrong. That was the idea back in the day, that apparently Maxwell's equations cannot be used for all observers. There is one particular observer for whom the Maxwell equations hold, and the other guy for him it does not hold. And then of course the question is, who is the guy for which it holds? But if you do actually mathematics, if you just go through all the equations that you apply this to this particular situation, you will find that if this guy is using the Maxwell equation and he finds how this electron in his hand will move, he will get exactly the same predictions as the guy who happens to be moving with the electron in his hand. Apparently the extra magnetic field that you pick up, because of going to this other frame, for some reason exactly compensates the fact that you are now in a different frame. You get exactly the same predictions. And people thought, well, that's maybe just a mathematical curiosity of the Maxwell equations. And Einstein turned it around and he said, no, maybe this is just a law of nature. You should be able to use the same laws of physics, in this case the Maxwell equations, regardless of whether you're standing still with regard to this thing that you happen to be calculating, or that you're moving. That there is no coincidence whatsoever. Nature is built this way. That every single person, regardless of how fast he is moving, is allowed to use the same type of mathematics. Now the numbers might look different because this guy only sees an electric field, no magnetic field, and this guy sees an electric field and a magnetic field, so the numbers per person might change, but the actual predictions, and predictions here meaning what acceleration the particle will feel in his hand, that the actual predictions are still the same. So Einstein made that a principle of nature, and he called it the principle of relativity. The laws of nature, you should be able to, or you should be allowed to use the same laws of nature regardless of how fast you're moving with respect to a certain experimental setup. He showed that it was just already built into into electrodynamics. The Maxwell equations as they stand have this already built in. Now there are also some laws of physics that do not have this built in. Most famously, Newton's laws. Right? If you change from one observer to the other in Newton's laws, you will change your predictions. Have you ever seen that before? Have you ever heard the phrase inertial frame, maybe, say in Newtonian mechanics, yes? Everybody's aware of what that means? What does it mean? What's an inertial frame? It's not a test, I'm just curious if we're talking the same language here.
Accelerating frame of reference.
With respect to whom? Acceleration is defined with respect to some other guy, right?
To an observer at rest.
Okay, but what is at rest? How can you
how
tell that somebody's at rest?
Rest.
Yes.
Yeah. As long as there's no acceleration, doesn't it matter like with the observer, because like if you have a constant velocity,
Okay.
it's also inertial.
Yes,
So
okay.
it doesn't matter like if you are in the box moving with it or outside and looking in the box moving, as long as it's like not accelerating.
Yes, I think you're in exactly the right direction here. Of course, the first thing that you think is, well, you know, if you're not accelerating, then you're in an inertial frame. Okay, sure, that's fine. How do you know whether you're accelerating? Well, you're accelerating with respect to rest. Yes, but how do you define rest? And I'm not teasing you. This is an actual question in physics. How do you know whether you are in rest or whether you are not in rest? I do agree that if you are in rest, then you can use Newton's laws. If you're not in rest, you cannot use Newton's laws.
Because you can test if you're accelerated or not.
How?
Force.
Okay. Give me an experiment. Suppose I want to know whether you are at rest. What should I do?
Probably like a spring.
And then, okay.
I don't know, maybe I would have like a horizontal spring and place like an object which like a round thing, for example.
Yes.
And if I accelerate in that direction, the ball should go backwards.
I
And
see.
then I should see like the spring contract or not.
Yes, that's actually correct. What you can use is the inertia of objects, right? Newton's first law tells you that if an object happens to be moving already with respect to something, it will tend to keep on moving with its straight velocity if there's no forces. But that means that if you want to know whether you are in a frame in which that holds, you just have to, I don't know, place an object here, and if it stays next to you, then it means apparently you are in an inertial frame, right? At the moment that you have to be in an accelerating frame, the thing will move backwards because Newton's law tells the thing that it wants to go with constant velocity, whereas you are accelerating, so you can actually see the thing move away from you. Now, I hope that this will give you a new interpretation of what Newton's first law tells you. There is a certain school of people, let's say something like this. Well, here's Newton's second law. There you go. That's Newton's second law. If somebody gives you a force, you can calculate acceleration. And then they say, well, but the first law is really just a special case of this one, because if there's no force, you have no acceleration, things move with a constant velocity. Hey, look, that's Newton's first law. No, 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 no. That might look true, that you can derive Newton's first law from Newton's second law, but Newton's first law does something, asks a more principal question. Namely, are you allowed to use Newton's laws in the first place? Because that only works in a non-accelerating frame. How do you know that you're a non-accelerating frame? If all objects move with constant velocities. So Newton's first law gives you a criterion whether you are in an inertial frame or not. If you find that things do not move in a constant velocity if there's no forces operating on it, that means you're not in an inertial frame, and that means that this law, the second law, you're not allowed to use anymore. So Newton's first law is not a special case of Newton's second law. What Newton's first law tells you is whether you are allowed to use Newton's second law. This is why it's a more important law than Newton's second law. This is why it's called the first law. And I really object to books that I read every now and then of popular science where it says, well, Newton's first law is only a special case of Newton's second law. No, it isn't. You cannot define acceleration without the Newton's first law. That's the idea. Now, the idea here was that we now know by Newton's first law what an inertial frame is. The idea now is, can you apply Maxwell's equations in all inertial frames? And the answer is yes. Again, just repeating myself here, if you go from one inertial frame to another inertial frame, and so you start moving with a constant velocity with respect to u, some of the electric field that I used to feel has now been turned into a magnetic field. And it's not obvious whatsoever that the predictions that come out of this extra magnetic field will give us the exact same experimental predictions as if I had been standing still, had only seen an electric field. But Maxwell's equations automatically make this work. Now, historically speaking, Einstein saw this. He saw, wait a minute, apparently there's this inherent property of the Maxwell equations that in all inertial frames, regardless whether you pick up magnetic fields or not, you will always get still the same predictions. In other words, that Maxwell's equations are valid in all inertial frames. That's the idea. Now, what we're going to do today is do some special relativity. Out of this criterion that the laws of physics should look the same, you should be allowed to use the same laws of physics in all inertial frames, comes all of special relativity. Now, this might not be the way that you've heard it before. Typically, when people teach special relativity is that they say, well, people found that the speed of light is the same for all observers. And as a result, you do some thought experiments and you get some laws out of that. Some laws between different time scales, right? You've seen this before. And Lorentz contraction and such. Do you know these formulas by heart, by the way? So here's some special relativity.
Time dilate, so you've got the factor, I don't remember
Okay,
it.
Lorentz factor.
Yeah, Lorentz factor.
Gamma.
Okay, so there's a gamma.
Gamma,
Okay.
yeah.
What else?
So, now it's when it gets tricky. So your time.
Yeah. How about this one? And let me just define what things mean. By d tau, I mean the amount of time that passes for somebody who's standing next to some event happening. Right? Suppose that he's, I have no idea, is there anything, any motion that you can do just for funsies? Okay, he's lifting up his bottle. Okay, so there's two moments in time there, namely the moment that he starts to pick it up and the moment that he reaches maximum height or something like that. Those are two events, the starting moment and the ending moment. There's an amount of time in between that. That amount of time we call d tau. I have to be very specific here. It means his amount of time, the amount of time that it takes him to lift up that bottle from the beginning moment until the end moment. That's called d tau. It's called the proper time, the eigentime. You have to be ridiculously careful what things mean in special relativity. It's called the proper time, or eigentime. And yes, that does come directly from German. This is the amount of time that passes for somebody for whom the two events happen at the same place. In Chai's case, that is the case, because the starting moment of his bottle lifting happens at the same position as the end moment. Not exactly, because there's 20 centimeters in between or something like that. But what I'm saying is he's practically standing still with respect to the bottle. So this is the amount of time between two events that happen at the same space, at the same position. Okay? Now, here I am again with my electron. Well, forget about the electron, it doesn't matter for this particular experiment, right? I mean, just walking here and I'm looking at him lifting that thing. I too see the same two events. I too see him picking up that thing and lifting it up. It also takes an amount of time as seen by me. But that amount of time is not the same as his amount of time. That amount of time we call dt. That's this one. The time between the same two events as here, between two events that do not happen at the same position. And I hope you all understand what I mean when I say not at the same position. Because as I'm walking here, can you lift that thing up again in slow motion maybe? Okay, slow motion, so, start again, okay. Okay, here's moment one, my position, that's, I don't know, 20 centimeters or something like that. Okay, keep on walking, there we go, you lift it up. Okay, he's at its final height right now. There's more distance in between now. That second moment is more meters away from me than that first moment. For him it was at the same position, well, apart from maybe the 20 centimeters of lifting it up. But for me there's an actual distance in between. Now, yeah, thank you. That amount of time is this number here. And yes, this is time dilation. Now I haven't derived this, but I will in a second. Maybe some more equations that you...
Wait, I have a question.
Yes?
So for someone that would be okay, it's not possible, standing on that bottle itself.
Yes.
Which T would you use then? That would
okay.
be this.
Well, there's a small experimental subtlety here.
Right.
Namely that in the bottle lifting itself there's also some space traversed.
Yeah.
So that's really not the point of this equation per se.
Okay.
But if we would take that into account,
Yeah.
then the guy standing on top of the bottle would actually measure this time.
Yeah.
And there is a slight difference with Chai, who is not standing on top of the bottle. Because for him that also happens at two distinct different locations,
Yeah.
the beginning and the end thing. So there is a small difference. So you know what, let's replace the bottle by him blinking his eyes.
Yeah, okay, that's right.
All right.
Yeah.
So we don't have this issue that even in his frame there is even some motion going on. But then you might say, wait a minute, this blinking is also some sort of motion. Okay, sure. But the two events, namely his eyes being closed, open, and then close again, well, that happens at the same position, okay? It's a very artificial situation here. Usually when I think about these things, I say exploding firecrackers or something like that, right? So he has two firecrackers here. One he lets explode, that happens at one position for him. 2 seconds later, the other one explodes, same position, no motion. The amount of time between the exploding firecrackers as measured by him, that will be the time. And if I happen to be walking along, then the amount of time that I see between the same two exploding firecrackers, that will be dt. And to make things extremely explicit, you all know that the Lorentz factor, the gamma factor, as a function of v, looks like this. Asymptotically goes to infinity, and thus at the moment that the relative velocity between me and Chai will be c, the speed of light. This number will be 1, exactly 1. So it sticks to 1 almost most of the time, except when you reach about, I don't know, 80% of the speed of light. This is when they start to diverge. But that means that as long as I'm not moving with the speed of light with respect to him, or close to the speed of light, this gamma s is 1 and his times is my time. Okay? This is why he and I don't have to argue with each other how long this lecture will last. It's the same amount of time, because the amount of motion that we have with respect to each other is much smaller than the speed of light. Now I haven't derived this. The whole idea of today is that I'm going to derive these things, but via different means than your usual thought experiments with the trains and the mirrors and the ones that you've probably seen in your previous courses. But we were doing some recap of special relativity, so is there maybe some other formula that you know from back then? Yes, go ahead.
Lorentz contraction.
Yes, how does that one look?
I think it's delta L over another delta L over gamma. Yeah.
This one, right?
Yeah, but still delta L for another one.
Okay, well then that is the next question.
Yeah.
Whose length is which one?
Like the one moving is on the left.
This is the moving L?
If I see someone moving,
Yes.
the length, I will measure here. It's like
That's right. That's exactly right. So I typically call this L0. That's the amount of length that a guy measures if he's standing still with respect to the thing that he's measuring the length of. Can I take you as an example again? Can you hold the bottle sideways maybe? Okay, there's a certain length of bottle. And he's going to measure how, just like this, he's going to measure how wide this bottle is. I mean, it's 20 centimeters or so. And that's L0, or delta L0. Now I come along again, and I also measure how long this bottle is, how wide it is, and I will measure a shorter distance. That's this number here. That's this one. So let's be very clear about what everything means, because most of the misconceptions of special relativity come from not fully understanding what every symbol means. So let's be very explicit about that. This one here is the length of some object as measured by someone standing still with respect to the object. Is someone standing still WRT with respect to objects. And this one is the length of that same object as measured by the guy moving with respect to the object. As measured by someone moving. WRT with respect to object. So there you go. This, of course, is what we call Lorentz contraction. There you go. And to make things extremely explicit, because you know that gamma is always equal or bigger than 1, it's equal to 1 if the velocity between the two observers is exactly 0. Do you know the formula for gamma? You've all seen this before, right? You've all done special relativity. So do you know by heart what the formula is?
1 divided by square root of c squared.
I hear square root and 1 divided by, so we're halfway there.
1 divided by
Plus, minus? Which one is it?
minus.
Yeah, there you go. There it is. And where v is the relative velocity between the two observers. Now, if you draw gamma, it will look like this. You can tell that if v is 0, if chi and I are not moving with respect to each other, then gamma becomes exactly unity. In other words, our length and our times are going to be exactly the same. If I start moving, the bigger v becomes, the closer it gets to c, the more I get 1 minus 1 itself. It will go to infinity. That's exactly this asymptote right here. This thing is always greater or equal to unity. And as a result, let's look at these two equations so we can really interpret them. Time dilation then will tell us, this formula, that dt, which one is it, bigger or smaller than d tau?
Bigger.
Bigger, exactly. Because it's d tau multiplied by a number that is either 1 or bigger than 1. And here it's the other way around. dl is smaller or equal to dl0. Now this one is easy to interpret, yes? It just means that the length that I measure, moving with respect to Chai in his water bottle, is going to be a smaller number than the length that he sees himself. That's the contraction part. Things look smaller. This one means that, what experiment did we have? Firecrackers, blinking eyes? Okay, let's do the water bottle lifting again, okay? The amount of time that you see between the starting point of your lifting and the end point of your lifting is the tau. It's a smaller number than I see. In other words, it takes more seconds for me to see you doing this performance. That's not a way of saying that time is going slower. It looks like he's doing it in slow motion because he says, well, it takes me 2 seconds. And I say, no, according to me, it takes 4 seconds. So it takes 4 seconds for him to lift that thing. That's not a way of saying that apparently, to me, it looks as if he's doing it slower than he sees himself doing it. That's time dilation. What is the cause of time dilation and or Lorentz contraction? I mean, we just postulated this is true for memory because of your previous courses. What is the cause, the physical cause?
The speed of light is same for all frame of reference.
Speed of light is the same in all frames of reference. Let's be more specific. Let's use inertia frames here, because if you go to an accelerating frame, things become more difficult. You need general relativity. So let's just focus on inertia frames. Frames that are moving with constant velocity with respect to each other. How do you know if you're an inertia frame? When Newton's first law holds. Okay. So some people said it's because the speed of light has to be the same number for all, something like this. Where's the light in his water bottle experiment? He's lifting up his water bottle. Why do I need light to determine that my time is more seconds than this?
So you need to observe the water bottle.
Oh, okay. So the light
takes time to travel from the bottle.
Okay. So there is some light involved, namely, in order for me to do this observation, the amount of seconds, the light has to travel to my eye. Yes. Is that the cause for these equations? Well, you could tell that by the tone of my voice, maybe that the answer is no.
Yeah, well, you can also use a ruler. The ruler says the same. Ruler has nothing to do with it.
Well, I mean, wait a minute. Well, I don't understand. The ruler part?
Imagine you would pass by the bottle,
Yes.
and at the point you are at the bottle, you just measure it, and
Yes.
then move on again, then you should have the same length.
Uh,
Like it has something to do with the light.
no, exactly. That's the point. Because I can, well, this experiment I can certainly do without using light, I think. Can't I? Now, it's a common misconception when people think about special relativity. This has to do with the fact that how it's usually taught, namely a thought experiment with mirrors and lights and everything. Right? I mean, this is usually how people do this. And you do get to the right equations, this one and that one, but it gives you the false impression that light for some reason has a role to play in all of this. It doesn't. I mean, really, it doesn't. This whole idea that you need light in order to get these equations in special relativity is completely flawed. You can get all special relativity without ever mentioning light or doing experiments without any light in it. Suppose that for some stupid, difficult reason I decide to measure the length of the water bottle by using, say, the weak interaction. Has nothing to do with light. I mean, maybe there's somebody who says, well, wait a minute, isn't the weak interaction connected to light because of electroweak, in case you've heard of this? Because there happens to be a connection between the weak interaction and light. Let's get that out of the way too. Let's say that I measure the length of the water bottle using the strong nuclear force. It will be an extremely difficult experiment to set up, maybe, but I could do that. There's no light involved whatsoever. I will still get the same results. Okay? So apparently, these results have nothing to do with light. Most notably, it has absolutely nothing to do with the travel time of the light towards my eye. That is a huge misconception that unfortunately lingers in special relativity. Has nothing to do with that effect. Now, to be sure, the effect does exist, right?
Retarded time that we were looking at.
Sorry?
Like, isn't that the retarded time?
Yes, that's the retarded time that Jacco introduced. That if things happen to be far away, of course it takes some time for that thing for you to be observed. So there is a certain delay in time. That's not the same as time dilation. It's a completely different effect. One very clear way of showing this, I think, is that suppose that it is due to travel time. Then you can switch the sign of this effect just by moving in the other direction. Let's be clear about that. Suppose that he's doing 2 blinkings of his eyes, or his 2 firecrackers or something like that, yes? And suppose that it is. The time dilation is because of time delay. It isn't, but suppose that it is. One firecracker takes 2 seconds, or I don't know, I have no idea, but a small amount, let's say it's, I'm at this distance that it takes 1 second, okay? But it takes 1 second for the first firecracker to reach my eye, and I make the observation, look, the first firecracker has gone off. And then I move happily to my second position, the second firecracker goes off. Wait a minute, it takes more time for that second photon to reach my eye because I'm further away now, right? So there would be some delay in time. I would say, look, it takes more seconds between the 2 firecrackers. But suppose that I do the experiment the other way around now. I move towards him as his 2 firecrackers are going off. Then the first firecracker happens now. The second firecracker happens when I'm closer by. So that would mean it would take less seconds for the 2 firecrackers to explode after each other. So this delay effect that Jocko talked about is direction dependent. This effect isn't. The time dilation effect happens regardless in what direction you're moving. One very clear way of seeing this is because it says v squared. It really doesn't care whether you happen to be v or minus v. So apparently, you observing 2 events at different times than he does has nothing to do with the light travel time. Again, that effect does exist, but that's not the effect in special relativity. When Jocko showed you what the formulas for that was, to add to the confusion, it turned out that it did look something like this, without the squares. And so that effect does still exist. But that's just a geometrical effect. It has nothing to do with space-time and the properties of time and space itself. To drive the point home one more time, you all know the Doppler effect. Okay? That is of this kind. Because if you're moving in one direction, you hear one thing, if you move the other direction, it moves in the other thing. But you also know about the stretching of light due to the expansion of the universe. That is of the second kind. Just to be very clear, huge misconception, these effects have nothing to do with the travel time of the photons. Nothing at all. So where do we get this from? That's the route that I'm going to take, of course. How was it told to you in the special relativity course? I mean, am I sure that these popped out at some point?
I think Chris used light, so he used the Lathrul experiment with like a moving light clock. We have a laser and then that moves like this.
That's the famous way of doing it, yes, and it's didactically extremely correct. Even Einstein himself did it like this in his 1905 paper. But he was very well aware of this misconception, and I think I mentioned this before, but he built into his thought experiment some fail-safe that removes the idea that it's because of travel time. So that's a more extensive thought experiment setup than I'm guessing Chris used in his lecture about this. But Einstein was aware of this. It does make it more difficult to read, because he introduces a second light clock, of which its timed travel, its delay, not the delay, time dilation, but its delay, counteracts the one of the actual thought experiment. So it becomes a more difficult setup. Now, fortunately, that second light clock, I don't know, got on the wayside at some point when people wrote books about these things, and now everybody thinks that time dilation is due to travel time of photons. There's nothing to do with it. Well, now, of course, this is something that was derived by Maxwell already himself. Remember that we had these equations for the vector potential and the scalar potential, and I showed you that the vector potential and the scalar potential obey this differential equation. Let's take the scalar potential. Right? And one of the exercises that we did a couple of weeks ago is that I said, well, this is always solved by an equation that looks like this. Almost like this. And then we made the physical conclusion that apparently whatever phi is, it is something that moves through space with the speed of light. This is a mathematical consequence of this equation. Interesting question. It moves with the speed of light, but with respect to which observer?
To all.
Yeah, but how can you, I mean, usually when you say if how fast something is moving, you have to say with respect to what?
Light always travels at the speed of light, no matter
Well, yes, that was the conclusion that was then drawn. But before people knew about the speed of light being the same for all observers, people looked at this equation and they said, wait a minute, we never put in with respect to what the field is moving, yet we find that it moves always with the speed of light. Well, if you've never had to put in with respect to what you are moving, then maybe the conclusion is that it will always move with the speed of light. Right? This is where this principle comes from, this idea. So historically speaking, the idea that in all observer frames things move with the speed of light comes directly from Maxwell's equations. Again, just to drive the point home, this equation that we derived this at some point, we never specified with respect to which observer, and as a result you have to draw a conclusion, apparently it's true for all observers. Okay? So historically speaking, people first came up with the idea, okay, apparently the speed of light is the same for all observers. Then they did their thought experiments in the Einsteinian way with the mirrors and the trains, possibly with the second light clock to counteract the misconception of the delays. And then they come up with these equations. This is how historically it was done. Okay, so this the whole of special relativity comes directly from electrodynamics, historically speaking. But later on, people found, wait a minute, it even works without electrodynamics. And that's the route that we're going to take now. Because the reason that I want to tell you how this works without electrodynamics and even without light is for the very simple reason that these results apply to all of physics. Not just electrodynamics, not just light, all of physics. So that means that the best I can do is offer you a derivation of these things that never needs any electrodynamics and or light, and as a result, the results that we're going to find, these equations say, will hold for all of physics. Okay? That's the reason that we're going to take this other route. There's a second reason, much more practical, and that is that if every time that you want to do special relativity, you have to think of some light experiment with a light clock and a mirror and a train, physics is going to be very difficult. It will be much nicer if we're just going to have the results derived once and for all of physics, so you never have to think about these thought experiments again. Now, this is what we're going to do. So we're not going to take as a starting point light has to be the same value for all observers. We're not even going to take the starting point that light exists. We're just going to take one thing and one thing only, and that's the following. Here I wrote down something. I'm guessing you have seen this maybe in the special relativity course. At some point Chris wrote this down, but I'm sure that he first did the thought experience and then later on showed that this is true. Yeah. Okay, we're going to go the other way. We're going to start with this and then derive everything else. In fact, this thing is enough to derive all special relativity, including the E's, mc squared and such, and all of this we're going to do today. Okay, now, as it stands, this is not physics. This is just a definition of this thing called d tau. It just says, well, you take the amount of time between two events, his exploding firecrackers, that amount of seconds you square, and you subtract from that the amount of space between the two exploding firecrackers. And you get this number, ultimately, and this number we call c squared times d tau squared. This is not physics, this is just me defining something. The physics comes in at the moment that you say that whatever number comes out is invariant. The error here means this is where the physics starts. This is just a mathematical expression. It becomes physics at the moment that you say what this mathematical expression obeys. And what it obeys is whatever number comes out, this number will be the same for all observers. Now, to make hopefully clear what I mean, is let's take the exploding firecrackers or you lifting the water bottle again. We already saw, can you lift it again, thank you, slow motion please. Okay, there you go. So there's a couple of seconds for the starting point and the end point, but for me there's also a couple of meters in between, right? So that means that I have some dx, suppose it's all x direction that I'm walking. I have a certain dx, a certain distance between the first moment of the process and the final moment of the process. And I have a couple of seconds. So I have dt and a dx. I have two numbers. I take these two numbers, plug them in here, plug them in there. There's no motion in y direction or z direction, so we can ignore these latter terms here for simplicity's sake. Some number will come out. What the number is, depends on your measurement, but some number will come out. Now Chai himself will also measure how much time it will take for him to lift that thing. What is his dx?
0.
0. Right? Because in x direction there's no a different position for his begin point and his end point of him lifting the bottle. So his dx is 0. He will also measure amount of time dt. It will not be my dx, because my dx was not 0 and his is 0. His dt is not my dt, so we have different numbers for dt and dx. Yet this particular combination, if both of us will calculate this using our own respective numbers, will give us the same result. That's what we mean by the word invariant. The same for all observers. Now, this claim that this particular combination of amounts of seconds and amounts of space, that is the same number for all observers, is enough to derive all of special relativity. This is where everything is going to come from. Is there any light in my claim here?
Speed.
There is a speed. There is a speed of light involved. I agree. What we have here is some number. It has to be a velocity for dimensional reasons, because this is an amount of meters, and you cannot add seconds to meters or seconds squared to meter squared. So just out of dimensional consistency, there has to be some velocity squared. By the way, I've never said it was the speed of light. I just say there is some number there to make sure that you can add these things together so they have the same dimensions.
But you are... no, okay, you're only assuming that information can't travel infinitely fast, right?
No, I've never said anything about traveling of information. Do you notice that when I make this claim about the invariance, I haven't said anything on how I measure my amount of seconds and my amount of space, whether I've used the photons having to travel to my eye, or this elaborate construction that I did with the strong nuclear force, say. I've made no claim whatsoever on how I do the measurement, how I got my dt and my dx. There's nothing of that in my statement here. The only thing that I've done is that, well, I have to add these things together in this particular way, and for dimensional reasons it has to be a velocity squared. I haven't even said two things. I haven't said what the velocity is, what the number is. We all recognize it as the speed of light. But suppose I've never made that claim. I also haven't even said that there is anything that happens to move with that speed. Do you agree with me that I could have written any speed there, and for dimensional reasons that would still be a true statement? I could even write this down, any velocity, regardless of whether there happens to be something in nature that travels with that velocity. I'm very sure that all of you look at C and say, "Oh, look, there's the speed of light." I've never made that claim. I just say there has to be a velocity there. If it confuses you, if it gives you the impression that I smuggled in light here, take some different symbol, V. Some specialized V that I haven't specified the number for, let alone that there is something in nature that follows that speed. Of course, we're going to call it C because experiment data tells us that it happens to be that there are things in nature that follow this speed. Not just light, by the way. Are there any other things that you know that happen that travel with this particular velocity? The gravitational waves is a very good example, yes. Very close to home as well, too.
Neutrinos?
Neutrinos, not exactly, because they have a little bit of mass, and things that have mass cannot move at the speed of light. Also something that we will see today, coming directly from this statement alone. But yes, to a high approximation than neutrinos. Gluons, the particles that tell quarks how they should interact with each other. Right? What the photons are to electrodynamics, this is what the gluons are for the strong nuclear force. They also travel at the speed of light. It's by historical accident that we call this particular number the speed of light, because it happens to be that light was the first thing that we saw that goes with this velocity. If in some other dimension people had first found gravitational waves before they found light, this would have been called the speed of gravity, or something like that. Right? What you have to distinguish for yourself is light that moves with a certain speed and things that move with the speed of light. Those are different things. It's only by historical accident that we call this the speed of light. For now, the only claim that I'm making is, for dimensional reasons, there is a velocity here in order to be able to add dt's to dx's. And that is up to experiment to tell you whether there is something that follows this particular speed. And again, it's only by historical accident that we call this the speed of light. Okay, my claim is, this is all you need to get all of special relativity. Now, before we do the derivations, let me tell you what the advantages are of doing this. First of all, you get rid of thought experiments. And this is not to diss other courses. It isn't. The reason that I don't like the thought experiments idea, it's didactically correct, but the reason that I don't like it is because it builds in misconceptions. You automatically think, oh, it's because of the speed of light that something special is going on here, and it has nothing to do with that. Also, it gives you the impression that all the rules come from the details of the thought experiment. Whereas, because I have made no claims about whatever thought experiment here, that means that whatever conclusion you're going to get is going to apply to all of physics. Just think about this for a second. If somebody derives these laws by using this one particular thought experiment, then logically speaking, that means that these conclusions should only hold for that particular setup. Yet the claim is usually made, look, we found this for this light clock thought experiment, but we're going to assume that it holds for all of physics. Now that is a huge step, that you find the conclusion for one particular thought experiment and then you say, oh, it applies to all of physics. One question that I typically ask to drive that point home is, suppose that you do this thought experiment with the train in the mirror, you do this underwater. Forget about how you would do this in practice, okay? Suppose you do this underwater. You take some laser light, you have this train underwater, mirror, train, everything exactly the same, but now underwater. Now you do know that light travels a little bit slower underwater, right? But if you go through the thought experiment, you will get exactly these same results, but with a slower speed of light all of a sudden, right? Because now you don't have the c or in vacuum, you have the speed of light in that thought experiment of light traveling through water, which is a smaller number than this c. But that would lead you to the conclusion that apparently special relativity depends on whether you do the experiment in one medium or the other. Whereas these rules apply everywhere, even underwater, with this speed of light. So this is what I mean. You very easily get confused that the experimental setup of your thought experiment has something to do with the results. All right. Enough introduction. Let's start. I'm going to derive a couple of things. One of them is time dilation. The Lorentz contraction is an exercise I would like to do this afternoon with you during the tutorial. It's algebraically a little bit more involved, but it's the same ideas. And then I want to say something about the Lorentz transforms. Now, at the moment that we have that, we will have all of this results on the left-hand board, plus some extra. I'm going to cast that into this one mathematical form of 4 vectors, and then apply the 4-vector formalism to derive for you that E is mc squared and such. And as a bonus, we will get the things that have mass can only travel with the speed of light. As a final bonus, I will derive that the speed of light will be the same for all observers, which usually is the starting point of the derivation of everything. So we're going to take this as our starting point, math, and end up with the statement that the speed of light must be the same for everybody. So then you can see that's completely equivalent to your usual way that you've seen this. All right, let's get started. Time dilation? Time dilation? this particular combination we call c squared times d tau. It pays to take a second to try to realize what d tau means physically. Mathematically, it means this particular combination of dt's and dx's and such, but what does it mean physically? But can you tell from this expression that this d tau is indeed exactly what I said a d tau is according to this text here? Time between two events that happen at the same position.
Couldn't it be dt as well?
What do you mean?
Does it really matter? I mean,
Yeah, it matters.
and what I mean to say is, isn't that tau supposed to be like for all observers the same?
I agree. Yes, that's exactly what I say when I said it's invariant. Yes.
So,
Well, it's an amount of time. Yes, d tau. Whose time is it?
I understand. Like moving, like in the same. But the event takes that same place, like as you're
Exactly.
still moving.
That's correct. That's exactly what I write there. The time between two events that happened at the same position. But how can you tell from this expression that that's the case? So go ahead.
So if you're not moving, then you like x, y, and z are like constant, and then you get the same, and dt is like d tau.
That's all there is to it. Yes. So as an observation, before we continue, if one observer sees two events happening at the same time, and the same position, excuse me, happening that means for that observer dx is 0, dy is 0, and dz is 0. Right? Dx is the amount of space in x direction between the two events, but if he sees it happening at the time, that means the amount of space between the two events is 0 for him. That's by definition of seeing things at the same position. Now, but that means that if you substitute dx, dy, dz is 0, you will end up that for this particular observer, this follows. Or in other words, that d tau is dt. Now dt is the amount of time that passes between the two events for that particular guy, and apparently that's exactly what d tau means. That's what you find now. So it's good to remember what d tau means. This particular combination gives you the amount of time between two events as measured by an observer who stands still with respect to the two events. Okay, good. Now I'm going to introduce this second observer. The second observer, here's that first observer, right? The guy who's standing still with respect to two things happening. We've now seen that for him, this whole expression reduces to d tau. The other observer, who is not standing still with respect to everything, will have this expression. I'm assuming that the two events happen for both observers at the same y and z position, just for simplicity's sake. The equality sign is exactly this invariance. That whatever comes out of this expression for the one observer, for that guy it's called d tau, it should be the same as what comes out of this expression for the other guy. That's this one. And the fact that this is the same is exactly the invariance statement over there. So this is what you get. Two things happen. One guy is standing still with respect to the two things. For him, this holds. And for the other guy who's moving with respect to the first guy, this holds. Now we do some math. I've divided c squared away, both sides. You know what? physics, just math. The first step I've divided the c squared away. Second step I divided away a dt squared. On the right hand side, yes?
Is there a reason why you, on the top expression, why you're using minus dx squared minus dy squared minus dz squared instead of plus?
Yes. The question, okay, the question is why are there minuses here?
Yeah, that's the question.
Okay, nature.
Oh.
Yes.
Okay.
At some point we have to have a starting point.
Yeah.
And nature has decided that the relationship between the dt's and the x's come within a relative minus sign.
Right.
I have no deeper explanation for this except for this is apparently what nature has chosen to do. Again, from here to here, this is just dividing away a dt squared, right? Taking it outside of the brackets. Notice what we have here, 1 over c squared. And I have dx dt squared. I would call it a velocity. Now, velocity typically you would write v squared. I'm going to ask you a question in a second about this, but first let's continue with the expression. And so we have d tau squared, the amount of time as seen by the guy who's standing still with respect to the two events, is given by some number times the amount of time for the guy who's moving with respect to the two events. If you substitute back in your expression for gamma, then you will recognize this as 1 over gamma squared. In other words, dt is gamma d tau. I've taken the square root of both sides and brought the gamma to the other side. Here. There it is. No thought experiments, no light. Just me taking this strange expression that nature has given us and did the math. That's all I did. No delay. I haven't said anything about, well, the light still has to travel to your eye first. Nothing of that has been built in. I haven't used any thought experiments, so the result is general. Two subtleties here. I took the square root here. And as you know, the square root of 4 is not just 2, it's also minus 2. So I've made a choice. Mathematics tells you it could be plus or minus. I've chosen the plus sign. Can you think of a reason why?
You can have a negative time if you're...
Oh, but it's not time. It's the elapse of time. It's a duration. It's not a moment in time. And I can have a negative amount of duration, right?
Can you?
Well, it's been minus 1 hour since this lecture started.
Okay.
So
Time doesn't flow backwards though.
there we go. By using the plus sign here, I've made the physical assumption that whatever this guy measures, whatever this guy measures, they both see time flowing in the same direction. So that's what I put in. There was a second subtlety here. I took dx dt and I called it v. Well, to be sure, a dx dt is indeed a velocity. But what velocity is it?
In the x direction.
Sorry?
It's only in one direction, right? It's in the x direction.
Well, that is, yes, okay, that is
Was
very
that what
true.
you pointed out?
No, that is true, because for simplicity's sake, I said that both observers still see everything happening at the same y and z. You don't have to make that assumption, it's just the mathematics becomes more involved. But you're right, so the v is indeed a v in x direction, because it's a dx dt and not a dy dt or a dz dt. But what is moving with that velocity? Something is moving with that velocity, apparently. Well, there are two observers, so which one do you mean? And if you say that one observer is moving with this velocity with respect to what?
To the other.
Okay, that is correct. It's the correct answer. It's the relative velocity, the velocity between one observer and the other. But how can you tell?
Inertial range.
That just tells you that you're in an inertial frame. It's a very legitimate question. I've introduced a velocity, but I haven't specified what velocity that is. I just said there's a dx dt, and I know from my mechanics that dx dt's are velocities, but whose velocity is it? Your answer is correct. It's the relative velocity between the one standing still guy and the other guy, but how can you tell from this derivation? It's not something you have to...
The one standing still is already in already d tau, so there's nothing really different. Right.
I'm not sure I follow the argument.
I don't. So the one that sees two events in the same position already has.
It's this guy, yes.
Yeah, it's already there, so he doesn't have x or y's or anything.
That is true. I mean, I've removed the x's and the y's and the z's for that guy.
So
I'm not sure it answers the question still.
So it has to be the other guys that is the one.
Okay, but then you still have what you're now saying is that, well, it cannot be this guy because this guy is now moving with respect to the two events. So by elimination, it must be the other guy's velocity. But velocity with respect to what? I mean, you're right, it is the other guy's velocity, but with respect to what? The answer is already given. It's with respect to the first guy. But how can you tell from just the derivation?
That ratio E over C.
Because it's like that guy's x and that guy's t, and not the other guy's x and that guy's t.
That just gives you that it is that guy's velocity, but it doesn't tell you with respect to what. It just tells you that it's this guy's velocity. Well, let's do the experiment one more time so you can just actually visually see it. Can you lift up the bottle again, or if you happen to have two firecrackers, make them explode? Or blink your eyes or something like that. Okay, you're lifting that thing, okay? The starting point here, thank you. What's the x now for me? I'm the moving guy.
0.
0, okay. Lift it up, lift it up. Standing over here. What's the x now?
X.
Well, I know, 1.5 meters or something like that, yes? So dx is 1.5 meters. Divided by the amount of seconds dt, whatever it was, 2 seconds or so. Do you see that this dx
Oh,
is
so
it
the x relative to the point that
yes,
you're traveling.
I'm measuring my axis with respect to the two events, which also is with respect to him, because he was standing still with respect to the two events, yes? So that means that the dx divided by dt is exactly the velocity with respect to the bottle, and thus with respect to chi. So this is why it's the relative velocity between the two observers. Now this completes the argument, because that then gives you exactly this rule, including the text underneath it. So there's that. I'm very much in the stressing things business today. No thought experiment, no light, nothing. So that means that this conclusion is completely general. Even if, if I did the measurement here with a strong nuclear force instead of light. So there you go. So that's nice. Now the time dilation, right? We've now shown that this indeed follows from that statement over there. I haven't made any other assumptions, did I? Just that statement that it should be invariant? Well, I made one maybe. Namely that there should be a plus sign, that time flows in the same direction for both. That's the only additional assumption that I made. The second one that we had to show is the Lorentz contraction. This is something that you can do during the tutorial. But just to give you a hint how we'll do this, how would you measure the length of this bottle? The width of the thing. How do you measure lengths? Okay. With a ruler. That's okay. That is very true. Actually, yes. Please tell me.
The time and velocity.
There you go. Thank you. This is one way of measuring this thing, the width of this thing. Of course, you can use a ruler. Of course, that's true. Suppose I take a ruler with me. Okay. Here's your ruler. Suppose I take this thing with me. I measure at what time the front of my ruler crosses the starting point of the bottle. I happily move along. I know what my velocity is with respect to him. At some point, I will have crossed the front end of the bottle, and there's a couple of seconds in between. If I know how many seconds there is in between this point and that point, and how fast I was moving, I can tell what the width of the bottle was. Now, if you do that setup, and then you take into account that the amount of time that I measure from the first point to the next point of the bottle is not his amount of time, because there's time dilation that we've already derived. You play with the algebra, you get this rule. This is something we'll do during the tutorial today. So let's assume for a second that we've done that derivation. That means that we now have both of these two results completely derived from only this statement. So life's good. Are these the only two relationships between times and spaces, let's be more explicit, between durations of one guy to the next and lengths of one guy to the next?
Mass also increases.
Sorry?
Mass also increases.
That is very wrong, actually. Let me get back to that in a second. I'm sorry, that sounded very harsh. That's not how I meant it, but that unfortunately is another misconception about special relativity, that mass increases with velocity. It doesn't. It really doesn't.
It's the energy that increases?
The energy does increase. And yes, there is a statement about mass and energy having some relationship with each other, but you cannot take the increasing of the energy, you cannot one-on-one map that onto the increasing of the mass. And I will give you an example of that later, how that doesn't work. Unfortunately, it's also something that has gotten into the common understanding of special relativity. It's not a matter of taste. You can actually explicitly show that this is not correct. So we will get back to that later. Other relations maybe? Between one guy's observations and the other guy's observations? Lorentz transforms. You've seen this, right? Do you know what they are? The expressions? I'm going to remove this. So we're going to take time dilation as given. It's derived. Lorentz transformation, the Lorentz contraction also. Where's my... What we now have is some relation between one guy's time and the other guy's time. We also have one relation between one guy's length and the other guy's length. My claim is there are more relations between one guy's time and one guy's length. Yes?
Oh yeah, as you said, like the Lorentz.
Yes. But do you know what they are?
Yeah, it's like, is it not like if you want to describe like one same event and they have like different coordinates and to
I agree.
go from one coordinate to the other and describe the same event?
That's completely correct. But do you know what the expression is, the mathematical expression?
I forgot.
Okay. Well, you are very right, by the way. I mean, yes, the Lorentz transforms tell you if some guy measures a length and an amount of time, what will that length and time be measured by the other guy? Okay? Well, you either know these things or you don't. I'm going to give them to you right now. The amount of time measured by one guy, I'm going to call this one guy with a prime, times c for dimensional reasons, is gamma times the amount of time measured by the first guy, plus or minus. The plus or minus is whether they're moving in one direction or the other direction. Let's take a minus for definitive sake. Times v over c. Here's one. So if two events are happening, here's the two exploding firecrackers again. And I measure how much time there is in between the two. I also measure how much space there is as measured by me. And I want to calculate how much time the two firecrackers explode after each other by measured by some other guy. I just fill in this equation, I will get the other guy's duration between the two firecrackers. This is for time. For space, almost the same expression. That's this one. If some guy sees two firecrackers exploding with 2 meters in between of them, and you want to know how many meters are in between as seen by the other guy, take the first guy's amount of meters and duration between two firecrackers, put it into this formula, I will tell you how many meters are as seen by the other guy. I have not derived these. I just tell you that they are like this. How were they derived before? I mean, I'm sure you've seen the derivation of this. Just out of curiosity that I'm asking now.
How were they derived?
Yeah, I mean, I'm sure you've seen these two derived before, but how were they derived before? Was that again a thought experiment maybe, or was it algebra?
I think it was algebra.
Yeah.
Yeah, I think we did a train.
Yeah, I guess.
How we train?
Okay. Again, you're very right. You can derive these, just like the time dilation or Lorentz contraction, you can also derive these two expressions by, again, using a well thought of thought experiment. But my claim was all of special relativity is encapsulated in this statement. So this should be as well, right? Now there's two ways of proving that this is indeed a consequence of this statement. One of them is by starting with this one and asking yourself, how can t's and x's of one guy be related to t primes and x primes of the other guy? And then trying to find the most mathematical expression, general mathematical expression that does the trick. And you will find these. If I were to give a course in relativity, I would go via that route. Now, there's a simpler way, and that is, well, take these as given, substitute them back in, and then show that if I replace these dt's, dx's, dy's, and dz's by these expressions, I will get exactly the same thing back, but then with primes. It's the difference between somebody asking you to solve a differential equation or somebody giving you a solution and putting it in to show that it actually solves the differential equation. We're going to take the second one. Again, this is an exercise later that I would like to do with you during the tutorial. That if you substitute these into this expression, you will see that it's indeed invariant. Now, before we're going to have a break, just a question out of, well, just to make sure that we don't have any misunderstandings. So let's assume that we've derived this, as we will do later. This one states that if I know my amount of time between two exploding firecrackers and my amount of space between the two exploding firecrackers, I can calculate how much time there was for the other guy between the two exploding firecrackers. So I can take my amount of time and calculate the other guy's amount of time. That's what this one, the first one, says. But isn't that exactly this one? Doesn't this already tell you some guy's time expressed in the other guy's time? So they sort of seem to be saying the same thing, yet the equations are not the same. Yes?
This one, if the other one is less moving.
Yes, exactly. Thank you. Okay, great. So we can move on. In this one, we assumed that one of the two observers was standing still with respect to the two exploding firecrackers. That was Chai in our example all the time. This one says that neither of them have to be standing still. So he has the two firecrackers exploding over there. I'm moving with respect to the two firecrackers. Let's say that you are too. So you're also moving with respect to the two guys. I take my time and I want to calculate what your time was. None of us are standing still with respect to the two firecrackers because only Chai was. That means that to relate your time to my time, I use the Lorentz transform. If I want to relate everything to his time, I use the time dilation. Two questions, yes.
What's the difference between d t prime and d tau?
Exactly what we're talking about now. This is exactly the key difference between that equation and that equation. D tau is the amount of time as seen by a guy who is standing still with respect to the two events. And d tau is, prime is any random guy who doesn't necessarily have to be standing still with respect to the two things.
But they could be the same.
They could be. So in case,
Yeah, makes sense.
in case this one guy is standing still with respect to the two firecrackers, let's see what happens. If, let's say that the one without the primes is the guy standing still with respect to the two firecrackers, what would his dx be? That's correct, yes. Do you all see this? If some, yeah, you mean I can see the face of understanding now. If some guy, if this guy happens to be standing still with respect to the two firecrackers, his dx is 0. Put your hand here. You get exactly the time dilation formula back.
That's pretty cool.
Yeah. So the Lorentz transform you're right, they really are cool.
Yeah,
Is the more general expression of these two. You see that?
Yeah.
Let's see if we can also find the Lorentz contraction from these general expressions.
I have
Yes.
a question.
Yeah, go ahead.
So this velocity,
Yes.
which velocity is that? Because there's two different velocities, right?
Yes.
One of me moving and one of
Yes.
him moving.
Yes.
So which one is that?
Okay, I took the example just a second ago that he has his two exploding firecrackers. I'm moving with respect to him. That gives us one V,
Yeah.
right? He was also moving with respect to him and his exploding firecrackers. Gives you another V.
Yes.
And then there is our relative V. It's the letter V that's in there.
Okay.
So there's a relative velocity between the two observers, and it so happens that none of us are moving with this. Mixing up my words here. Short answer: the V that's in the Lorentz transform is the V between the two observers.
Yeah. Okay.
And there's no V in there that says something about how fast I am moving with respect to him or how fast he is moving with respect to him. It's only our relative
So
velocity.
it's both V's, so also in the
Yes.
gamma effect.
Yes. Now, so we saw that the time dilation is only a special case of this more general expression here. Can we see maybe if the Lorentz contraction is also a special case of this one then? Because what this one tells you is if I measure how wide two things are apart, and I want to measure how the other guy thinks, I want to know how wide the other guy measures the two things are apart. My claim is that's this expression. I take my width, do the math, find the other guy's width. But that's already this expression, right? One guy's width calculated as the other guy's width. So what's the difference? Both seem to be giving you the same information. One guy's width calculated to some other guy's width. Yet the expressions are not the same, so there must be some difference.
Isn't it the same as before? That maybe both of them are moving, so the...
That's correct. That's very correct. This expression holds if both observers are moving with respect to the water bottle. Okay, none of them is standing still with respect, but suppose the one of them is standing still. Can we algebraically connect this one to that? How do we do this?
The V becomes 0.
V.
Like this?
Isn't it dt that becomes 0?
Why would be dt that becomes 0?
Oh no, never mind. No, it's V.
It's not v that becomes 0
No,
because
it's not.
v is the relative velocity between the two guys looking at the water bottle, right?
Oh, yeah,
right.
No.
And at the moment that one of them starts to stand still with respect to the water, that still means that our relative v is still non-zero. So it's not the v that becomes 0. There's something else that goes on here.
Yeah, dx.
Sorry?
dx. X.
Yeah, this one becomes 0?
No.
This one?
Yeah, really?
But that means that the water bottle has a width of 0 for one of the two observers.
Okay.
Does the dt become a d tau?
Well, we have to be very, it might, but we have to be very clear what it is that dt means in this particular experiment. Remember that I said before how you measure the width of a water bottle? You could do it by just measuring the time, times velocity. All right? Now suppose that a water bottle comes flying by me, all right, and I want to know what its width is. Can I have your water bottle? Thank you. You will get it back in a second, okay? Standing here, and I want to know the width of this water bottle, and it happens to be flying by. Okay, and I want to measure the width of this thing by measuring time. So what I do is, I register at what point the front end moves past me, and I also register at what point the end point moves past me. Okay? Now, if I want to know the width of this thing, and I measure the front end, and then I wait a second, and then I measure the back end. Do you agree with me that I'm not measuring the width correctly? Let's take a second to parse this more correctly now. Width of the water bottle. If I want to know how wide something is, I have to measure where its front end is and where its back end is, and then take the difference between these two, right? That's the width of a thing. Of course, you use a ruler for this usually. Okay. Now, if the bottle is standing still, I can measure where the front end is, take my sweet time, and then measure the back end. Because the thing is not moving anyway, so I get one coordinate, get the other coordinate. The difference between the two is the width of the water bottle. Okay, if I'm standing still, no issue. But now the bottle is moving with respect to me. I measure the front end. Can I take my sweet time to measure where the front end is now? If I wait a second before I measure the second part, do you see that I do not measure the width of the thing anymore? Here's one point. If I want to know the correct width of the thing, I have to measure the back end. But if I wait a second, the back end all of a sudden is here, I measure a length that is too short. So if I want to measure the width of this water bottle correctly, how much time should I take between the two measurements? 0. So if I take my two events as measuring the front end and the back end, how much time should there be in between the two events? 0. So that means that I make my dt 0. If I'm the guy who get a flying water bottle and want to measure its length, you don't want me to wait a couple of seconds before I measure the front end and the back end, because in the meantime the thing has moved along. So in order to measure the length correctly, I have to make my dt 0. There you go. Now this is the dx that I was measuring. The guy who was seeing the bottle move.
Yes. And then that'll be shown.
Yeah.
And then you bring the gap to the other side to get it in this form, you get exactly this. So, long story short, then we're going to take a break. I assumed this. We got time dilation just by doing the math. I haven't shown you in detail, but we will later. You can also get the Lorentz contraction. We will also show during the tutorial that this is the more general rule, and we've seen how this one connects to these two. This is the general one, where none of the two observers have to be standing still with respect to the two events. But in case one of the observers is standing still, these two produce to the simpler ones that you have here. Again, no thought experiments, just this expression in math. That's all. Break time? God, time flies. Relativity jokes? No?
I was thinking about it.
Second chance to make a time dilation joke maybe now? No one? No? Alright. Well, let's recap. Claim these two equations indeed fulfill the requirement that this thing has to be invariant. We haven't shown that yet. We will do so in the tutorial. There's more equations that relate one guy's coordinates space and time to the other guy's coordinates space and time that fulfill this requirement. Namely the following.
The interval?
Sorry?
The interval? That one? Interval.
Yeah, I heard the words, but I'm not sure how that answers the question.
No, I'm just asking if that one also relates to this somehow. Because I remember it from relativity, but not really what it is.
This is what we call the interval.
That's
Yes.
not, oh really?
Yes.
Ah.
What did you think?
I thought it looked a bit different, but never mind.
Oh no, that's fine. Let's be sure that we use the right words here. This thing, this particular combination is what we call the Minkowski interval.
Okay.
Or for our American colleagues, the Minkowski interval. I'm not sure if you're one of them, but American people tend to call this the Minkowski interval. Or the line element. But this is all these words. Typically, people just call this the line element, and that's what I will use too.
We learned it as ds.
Oh yeah. Well, that is okay. That's a good comment as well. The way that I wrote it down is with the tau squared, but in some authors prefer to use ds. Now ds is not the same as d tau. ds is minus c squared d tau squared. It will not change any of our results so far. It's just redefining this thing in a different symbol. Now which one you use is really just up to the author. There's no difference in physics. It's just a different label, different name for the same thing. The reason that I tend to use d tau and not ds so much is for the reason that this one has a very clear physical interpretation, namely the one that we saw before, that this one is actually up to c squared, the amount of time measured by a guy standing still with respect to two events. So I prefer to use d tau over ds. But again, you can do the same physics. If this is invariant in d tau, it's also going to be invariant in ds, yes? So all physical results are still the same. It's just I tend to call this thing by the name that has the most physical interpretation for me. So don't think too much of it. Okay, so but my claim was these are not the only transformation between two observers' times and spaces that make the line element invariant. Using the right nomenclature here now. There's more. Some of them are very simple. Just going to give them to you. One of them is that you say, well, if you take one guy's time and you just define it as the other guy's time plus a certain fixed amount, let's call it dt, where this is a constant, this will also work. Do you see that this is the case? While you think about this, let me also write this down for the other coordinates. Where all the deltas here are constants.
How are they constant?
Sorry?
How is, for example, delta t constant?
Oh, that's simple. Suppose that I'm sorry, I just made this. I'll get to your question in a second. It's not the d's. It's the coordinates themselves. So suppose that you're coordinate the guy with you use prime coordinates, and I'm the guy using the non-primed coordinates. Yeah. And this one means that your watch and my watch are 1 hour ahead of each other.
Yeah, I was just thinking that there maybe should be an element of speed in there.
Why?
Because the difference of t that we measure would depends on the speed you're moving.
I don't see why that would be the case.
I mean, it would be different if you're moving at half the speed of light.
You mean that our times are different?
No, but that the difference in our time is going to be different.
Oh, wait. The differences are in the duration between two events. These are not durations, these are moments in time.
Okay, yeah, okay.
That's a different physical interpretation. There's a difference between the time at this moment, that's
yeah,
a t.
I was just reading it wrong.
Yeah, that was my mistake. I called this dt as if I was talking about the duration. I meant actual moment in time. It's very important that there's a difference between these two things. When I ask you what time it is, and you tell me it's 3:15 or something like that, that's a t. But if I ask you how much longer this lecture will last, you will say 15 minutes, that's a dt. And these things, special relativity, does not relate t's, moments in time, to each other. It relates durations of time, delta t's. Now my claim here is if I take your moment in time, and I take my moment in time, but there happens to be some difference in between that moment, I say it's 3:15, and suppose that you're at daylight saving time and you say it's 4:15, then that means that your t is not my t, there's an hour difference in between us. But it's a fixed amount. Do you see that the difference in how long this lecture will last will still be 15 minutes regardless if we're using daylight saving time or not? In both of our cases, even though he has a different t than me, our dt's are going to be exactly the same. Right? And the same with space. If I ask you how far away, I don't know, my cup of coffee is, you say it's 3 meters or so, 4 meters. So that's your x primed. And I say, no, look, it's only half a meter away. Right? Yeah. Then the difference between your 4 meters and my half a meter is 3.5 meters, that's delta x. Now, I hope it's very clear to everybody at the moment that you make dt's out of these and dx's out of these, that turning this into a duration will set these to 0. Do you agree with that? That's a statement I made just a second ago, that if I ask you how much longer this lecture will last, 15 minutes, that will be the case regardless if you start out with daylight saving times, 4:15 or 3:15. In both cases, the lecture will still have only 15 minutes. So somewhere in changing my time to your time, durations will not feel that time difference. So, long story short, these also leave this invariant. If I replace all my dt's by t primes, all of these will vanish and you will get the exact same expression back. So apparently this also leaves this thing invariant. Now we already had a name for this one. This we call the Lorentz transforms. And these are called the translations. Just translations in time and in space. Now, you can ask the mathematical question, have we now exhausted the amount of ways that I can relate my coordinates to your coordinates in such a way that it leaves this invariant? There's one more that you can do. Thank you. I can see by the gesturing that you know exactly what I'm going to say. Rotations. One other possibility is to say, well, you know what, the amount of time that I measure is exactly your amount of time, so this has not changed. But I'm going to replace my dx is going to be your dy. That's possible, isn't it? Distance to my coffee cup. And this is my x direction. Let's say it's 3 meters or so. But some other guy, let's take a random person, there you go. This happens to be your y direction. Now, if I change my dx by your dy, and at the same time I replace your dy by my dx, in other words, I replace this one by this one, that doesn't change the final expression at all, does it? What I'm talking about now is a very special case of a rotation. Let me just take myself an example. Here's my coffee cup, here's my x direction. Yeah, it's 2 meters away from me in x. It's 0 meters in y direction. But you know what? I'm going to change my x's and y's around. My x direction to my coffee is now 0, but my y direction is now the 2 meters that my x direction used to be. Do you see that the actual distance to my cup of coffee has not changed at all? It's just what used to be x is now y, but apart from that nothing has changed. Now, in this particular case, I rotated by exactly 90 degrees. You don't have to rotate by exactly 90 degrees. You can also rotate by, here's my x direction, 45 degrees. My cup of coffee is now a little bit in x direction, a little bit in y direction. Has the distance to my cup of coffee changed? The actual distance, no. So apparently you can rotate as much as you want and still always have the same distance to your cup of coffee. Now if you look closely, you will see that you recognize that this part is just Pythagoras theorem, isn't it? Gives you the distance to your cup of coffee. Now you can rotate as much as you want. You can change x's into y's by a certain rotation. The actual amount of difference, the x squared plus the y squared plus the z squared, will always be the same number. So generally, as long as you don't meddle with time, leave the time the same, you can do a rotation and you will not have changed this particular combination. How do we write a rotation, do you know? Let's say a rotation along the z-axis, so only x's and y's are changed, so my dz will still be the same. Do you know the expression? Yes?
Times cosinus or sine, sinus.
Yes. You might recognize this expression from mechanics. Here you see that I can turn my original dx into a little piece of my new dx and a little bit of my my dy. Have you seen this before? You have? This is what in mechanics you would call a rotation. You literally rotate your x and y axis by a certain angle, theta in this case, and you will see that your x direction has now become a certain amount of y direction, a certain amount of x direction, and it goes exactly via cosines and sines in this particular way. If you doubt this, just draw it out. Make a picture of this thing, do some sines and cosines, you will see that this is the correct expression. These are called the rotations. Now we've now exhausted all possibilities. These three are the only types of coordinate transformations between one guy's coordinates and the other guy's coordinates in such a way that this thing remains invariant. Now, we are only going to be interested in this one, because this is the one where time actually changes. Note that here time does not change. Well, moments in time change, right? Daylight saving time and such, but durations do not. Here, explicitly time does not change, durations. So if you want to do special relativity, where you're actually looking at how much time it is going to be passed for some guy next to the other guy, then you need these. So these are the ones we're going to concentrate on. But just for completeness, these are all the possible transformations between one guy's coordinates and the other guy's coordinates that leaves this Minkowski line element invariant. So there you go. Okay, we've derived special relativity, well, most of it. We've got the Lorentz transforms, and as we also got the time dilation and the Lorentz contraction. Anything else from special relativity that you might remember from previous courses? We heard something beautiful about masses before that did or did not become heavier as things move faster. Any other relation maybe that you might know from? Which do you know what it is? This one? That's correct. It's the relation between how much energy one guy sees expressed in what the mass of the object is that he's looking at times how fast that thing is moving. That's what your P is, your momentum. How was this derived in previous courses? This expression, the relativistic energy equation.
I think it was Chris took like a tube and a photon was emitted between the two.
Oh, okay.
The tube.
All right. Again, this is how Einstein did it. He had another paper in 1905, one in which he derived the Lorentz transforms and such, and one additional paper in the end by the end of the year where he asked the question, it was actually the name of the paper, does the energy of an object depend on its inertia? And that's exactly that experiment. He shot a photon around in some tube and then saw that the inertia changed. And then he said, oh, but that means that there's what he lacks in energy because there's a photon being sent out, he must compensate by mass. And then he came up with a version of this expression. That's true. Again, a thought experiment with a photon. The expression is much more general. It also holds for things that have nothing to do with photons. This expression also holds if you're not looking at tubes that have photons floating around. Okay? Claim. It's all in here. Yet again. Now, that might be a little tricky to see because note that there's no energies in there, let alone masses. So I'm going to get this out. Well, let's park this for a second and let's get back to it in a second. Because in order to derive this, I have to give you a mathematical theorem, one that we can prove immediately. And I'm going to need some space, so let me erase this. There you go. do it in 4-vector notation. Yeah, let's go and do that. Before we get back to that one, it pays at this moment to introduce some new mathematical notation. Same physics, no changes, just the notation is different. The notation is going to make all of the results we're going to derive from now on, including next week and the week after, much more easy. So, as a side step, new mathematical notation. Here it is. We're going to introduce this thing here. Out of curiosity, have you seen this before? What that means? I know that you have. Project period and such. It's a shorthand notation. We have dt's, we have the x's, dy's, and dz's. And you can write them all as this one big column vector. Like this. This we call a 4-vector. Now, a 4-vector is not just a list of 4 numbers in a column. It has a special rule. A 4-vector, by definition, is any vector. It's called the general one, A mu. And A does not necessarily correspond to vector potentials. You know what? Maybe we should just write a different symbol for this, not to get confused. Any letter that has your preference? That's not called phi either, or E. I was thinking about B, but then again you have the magnetic field. Let's not use that. Sorry? W. Sure. Okay. So what I mean by this is, it's 4 numbers. And they're all written in this vector thingy, yeah? Now, again, notation-wise, we label the 4 components by numbers. 0, 1, 2, 3. It does not say w to the power of 0. This means the 0th component of the w 4-vector. Why the 0th? History. They also could have called it 1, 2, 3, 4. They decided to call it 0, 1, 2, 3. Now, I was defining for you what a 4-vector is. I say it's any vector that you can write in this way. And here's the defining characteristic that obeys the following rule. We've seen that numbers typically change from one observer to the next. Right? The amount of time that one guy measures is not the amount of time that the other guy measures. The amount of space that one guy measures is not the amount of space that the other guy measures. Now, if I go from one guy, one observer, to the other observer, that means that these 4 components of one observer are going to be different numbers than the component of the other guy. Alright? Now, a 4-vector is by definition there's a minus. One that obeys the following rule. You have difficulty parsing this, what it says?
Isn't that the same as the integral?
Yes. Yes. I've put some primes here. That's the other guy's numbers for the same 4-vector. Okay? One guy's W1 is not the other guy's W1. So I distinguish them with a prime. One guy's W0 is not the other guy's W0, so I distinguish them with a prime. And for all these coordinates, the same thing. This number might be different from one observer to the other observers. This one might be different than this one might be different than that one might be different than that one. But this particular combination is the same for all. Okay? Now what is a 4-vector? A 4-vector is any 4 of these numbers that if you go from one observer to the other observer, this particular combination will be the same for both. defining characteristic is this equality sign. That if you go from one guy's observer frame to the other guy's observer frame, then this particular combination will be the same number for both. Let's make it explicit. We've never specified what W is per se, but suppose that there is some observable called W and it comes in with 4 components, yes? I'm not going to specify what it is, just keep it abstract. You have measured in your experiment W0, W1, 2, 3. I come walking past, I look at your same experiment, I measure what my W0, 1, 2, 3 is, signature with the prime because they're different numbers. My W0 is not his W0, my W1 is not his W1, etc., etc. But our particular combinations of these W's in this way is the same. That's this exclamation mark here. At the moment that the 4 numbers W have this property, then we call that a 4 vector. Do you have difficulty parsing this? So, question. If this is the definition of a 4 vector, how can I calculate my W's if I know his W's? What is the mathematical rule that connects his W's to my W's in such a way that this thing is the same for us both? It's the same, what do you mean?
If you have his W's, you have your torsions.
No. Do you understand the question here? It's very important. The question is, if you have his W's and you want to calculate what mine are, but you know that the connection between our W's is in such a way that this is invariant, that this is the same for us both, this particular combination. How are his W's related to my W's? It's already on the board somewhere.
The Lorentz transformations?
The Lorentz transformations, exactly. What we saw here is that this particular combination is the relationship that makes sure that that this particular combination of squares is the same for all. Do you agree? We haven't explicitly derived it yet, tutorial and such, but that was the claim that if you connect the dt's, dx, dy's, and dz's of the 2 observers in this way to each other, then this particular combination will be the same for both. Well, that's exactly this thing, isn't it? This thing being invariant under these transformations, that this means that this thing should also obey the Lorentz transforms. Let me make it very explicit. Maybe you can. How should W0 primed be expressed in the other guy's W's? Let's make life a little bit more simple. Let's assume that the motion between us is only in x direction, so that means that these 2 should be the same.
Does it need gamma?
There is a gamma in there, that's true.
So we just replace them. It's the same.
As in, just use these?
Like CDT squared is W0 and then.
So you're proposing this. Just use those rules. Was it phi over c? Like this?
Yeah.
And then this one would be this. The only thing I've done, or that you've proposed, is that you said, well, if we know that these transformations keep this invariant, then these transformations should keep that invariant. And that's correct. So that's a 4-vector. It's not just 4 numbers written as a column, it's 4 numbers that if you will go from one observer to the next, then the other guy's values for the number should be given by these rules. So what is a 4-vector? 2 equivalent statements, just repeating myself now. 4-vector is there you go. Right. This is its definition. Equivalent statement is exactly the same statement, or any questions at this point? Because this definition is going to be extremely important to derive expressions like these and everything that we're going to do in electrodynamics later on. You have to really know cold what a 4-vector is. So again, 4-vector, any 4 numbers of which this particular combination is invariant if you go from one observer to the next, or equivalent statement that you can calculate one guy's components to the other guy's components using the Lorentz transforms. That's a 4-vector. I think we're going to need a break now. Let me take Chai's question. Yeah, I know there's still 2 people missing, but let me take Chai's question anyway. He asked me. Forgot what the exact phrasing was of the question, but it had to do with the. Oh yeah. Okay, I remember now. Another misconception about special relativity. I hope I'm tackling a couple of them now. One of them was, no, it's not a light thing. It's a complete space and time thing. Everything follows from this. Another misconception is, oh, special relativity you can only use when you're looking at things that are moving with constant velocity, right? There is this one-on-one mapping that people have when they think about special relativity. They think, oh, special relativity has to do with constant velocities. There is a grain of truth in there, but if that were the case, then special relativity has an enormously limited application range, okay? Because you can only look at things that are moving with constant velocity, and there are not many things that move with constant velocity. Or standing still. Well, there are many things that are standing still, but you know, there's hardly any physics there. That's a misconception. Special relativity you can apply to things that are moving with a non-constant velocity. We do this all the time. And in fact, as Janko, when he does his calculations for what happens in the LHC, that's a highly accelerating system, right? It's a particle accelerator. Even if they're moving with a constant velocity through the circle, right? It's a 23-kilometer circle underneath Geneva. Even with a constant angular velocity, it's still accelerating in the sense that it's moving direction at every second. Now, still Jacob can use special relativity to describe everything that happens there, and not just by approximation, exactly. So what is the misunderstanding here? Can you use special relativity to describe accelerating particles, or can't you? You can. But then what exactly is meant with that mapping that special relativity has to do with constant velocities?
The inverse.
Exactly. The observer has to be in an inertial frame. The observer has to be moving with a constant velocity. The thing he's looking at does not have to. So that's a huge misunderstanding that people have. Oh, you can only describe things that are moving with constant velocity. No. You can describe everything in special relativity as long as you, the observer, are in an inertial frame. At the moment that you yourself are not in an inertial frame, this is the moment when you have to go to general relativity. Question. How do you know if you are, you, the observer, not the thing that you're looking at, you, the observer, how do you know that you, the observer, are in an inertial frame? How do you determine that? See beginning of lecture today. By Newton's first law. So let me stress one more time how important Newton's first law is. Not only does it tell you when you are allowed to use Newton's second law, it even tells you if you have to use special relativity to describe the world around you, or if you have to use general relativity. If Newton's second law breaks down in your observer frame, that means you cannot use special relativity. You have to use general relativity. Newton's first law is ridiculously important in all of physics. That was the comment that I wanted to make. The reason that we came up with this idea, can I use your water bottle again? Suppose this is a rocket, okay? And we're observers, we're going to observe the rocket as it launches itself into space. There's an acceleration going on there. As long as I'm in an inertial frame, I can describe the launching rocket just by using everything that's on the board now. Special relativity, no general relativity. It's not completely true because of curved space-time and gravity and such. Let's ignore that for a second. Okay? Then Chai came along and he said, oh, but wait a minute. Suppose now that instead of me on the ground describing the launching rocket, I'm going to be the rocket and I'm going to look at the ground that's accelerating away from me. I'm going to swap the two observers. Can you see that in the first case, the guy on the ground looking at the rocket, that guy can use special relativity, but if you swap place, then you stand on the rocket and you look at the ground accelerating away, that guy has to use general relativity.
I have a question about that.
Okay.
Oh, never mind, it's because he's more.
Okay. You're not convinced?
No, not exactly.
Okay. Do you know where the difficulty is?
I mean, how do you actually know that you are not accelerating?
Newton's first law.
Yeah.
So, if you want to know if you are in an inertial frame, or in other words, if you're allowed to use special relativity, what you can do is, I don't know, take a little dinky toy car, give it a little push. If the motion is along Newton's second law, then you know, oh, it's an inertial frame. If you're in a rocket, I can tell you right now that if you then push a couple of dinky toys around, they will move differently than they would on Earth because of the acceleration. So that means that you can determine whether you are in an accelerating rocket or on a stationary Earth. You can tell if you are in an inertial frame or not. And that means that Chai's objection, or his idea, wait a minute, you might as well just swap the two observers around, is not allowed. One observer is in an inertial frame, he can use special relativity. One observer is in an accelerating frame, he cannot use special relativity.
Okay.
Anyway, so that was, I hope that is a misunderstanding that will never get back to your mindset again. Special relativity can be used to describe accelerating things as long as you yourself are not accelerating. Yes?
So in the example of me looking at someone rotating at like half speed or something.
Okay. Then you can use special relativity.
But how would what effects would take place? Do I just, I don't see how the rotation would incite a time dilation or Lorentz conjunction.
I removed the gamma factor. In the gamma factor there's a V, yes? That V is perfectly allowed to be time dependent. What you could do, and after that I will just continue with the with our blanking on words right now. I will take your example and then we'll continue with the main story. Main story, that's what I was looking for. The gamma contains a V, and the V is allowed to depend on T. Okay? But that means that suppose that you have this one here. The dt's are infinitely small durations between two moments in time. Now usually you can turn this into finite amounts of time by just integrating both sides, yes? So if you just integrate all of this, you'll get finite amount of duration between one guy and the other. But I have assumed now that this thing does not depend on time itself, so I can take it outside of the interval. If the thing that you're looking at is rotating, then that means that the V in here is time dependent. You cannot take it outside of the integral. And your equation will look something like this. And then depending how your V looks like, you can just evaluate the integration and proceed as usual. Anyway, you also have a question?
Yeah, but it's probably quite stupid.
Okay.
So isn't the Earth also accelerating?
Yes.
So we're not technically an inertia.
No, that's true. That is true. So my example with the launching rocket is not entirely correct because the Earth is not an inertial frame. Now I told you that Newton's first law tells you whether you are in an inertial frame or not. And you just push a couple of dinky toys around, and if they move in a different way than you would expect by Newton's laws, then you know that you're not in an inertial frame. We don't have to push dinky toys around, you can just look at the clouds. Because the clouds do not go in a straight line with constant velocity, they have a Coriolis force, they go in this circular form. So they don't follow Newton's second law. So just by looking at the clouds itself, you can tell the Earth apparently is not an inertial frame. But by good approximation it is. All right, what we were doing, we have a couple of mathematical steps, but I do have to finish this story, so if you will indulge me for a second more. We just defined what a 4-vector is. Now remember, what we were doing was just recasting what we already know, no new physics, just written in new mathematical form, because that mathematical form is most adept for later applications. This is a 4-vector. Here is a claim that I'm going to make, mathematical claim. If you take a 4-vector, so we know that it's a column of 4 of these components and that it would transform in this particular way. And you would do the following. You would take another 4-vector, let's call that one V, and you make this particular combination. You take the 0 component of W, you take the 0 component of V, you multiply them together, you add to that the 0 component, the 1 component of W, the 1 component of V, multiply it together, add that to it. Let me just write this out. This is shorthand for this. Waiting for somebody to make an objection.
Dot product in between the two?
It is sort of like a dot product, but not quite, isn't it?
Plus or minus?
Ah, there we go. All right. It's very much the same question that you asked before. There are all of a sudden there's these extra minuses, and if you ask me why that is the case, the only thing I can say, nature. Okay. Now. Just bear with me for a second. This particular combination with a plus here and minuses over there is itself invariant. That's a claim, a mathematical claim that I'm making right now. Now a dot product, Scott, it was you, right, that asked that? A dot product would only have pluses there, and then this wouldn't work. In this particular combination, with a plus here and minuses here, this particular combination is invariant. It's a claim that I'm making, and we'll prove that in a second. It looks like this, doesn't it? You see that? The difference is that over here, we had dt, dx, dy, dz. There would be only, there's no 2 4 factors that you're doing this with. Right? There's only dt's and dx's and dy's and dz's. Here, I'm taking 2 different 4 factors and making this particular combination. My claim is that if you know that that w is a 4 factor and you know that v is a 4 factor, then this particular combination will also be invariant. Can you see why that is the case?
Because you could just call that one 4 vector, kind of?
No, you can't. I'm sure you mean something like this. What would be the next letter in the alphabet? Capital X or something like that? Yeah. You say, well, we call this capital X 0.
Yeah.
And then capital X 0 minus capital X 1, capital X 2, 3 is exactly like this form. And you know that this is invariant, so that should be the same thingy or something like that.
Yeah.
Unfortunately, that doesn't work because you don't need capital X 0, you need capital X 0 squared. You're missing your squares. So it looks the same, but it's not quite the same. So we still have to actually prove that this is the case. How to prove this? Suggestions. This is one of the exercises that I wanted to do with you, so let's make it interactive. How would you prove that this is the case?
We want to prove if it's invariant or if that is true.
That it is invariant. We want to prove that this is the case.
So maybe we want to do the Lorentz transform.
All right. On which one?
The right hand side.
This one?
Yeah.
Well, we do know how the W's and the V's themselves transform, don't we? I mean, given that they are 4 vectors.
Yeah.
And by definition, a 4 vector transforms like this. Now, if we know that the W is a 4 vector and we know that V is a 4 vector, that means that if I replace all my W zeros by these, and I replace all my V zeros by the corresponding one with this, and also with the omega 1s and the V 1s, then I get this huge new expression. Just do the algebra, and then find that all the gammas and everything disappears, and just get the same expression back. Then I've proven that it's indeed invariant, that it's the same value for all. Now we can do this in matrix notation, that's by far the easiest way, or we can just actually write it out. The writing out part is more clear, because I don't have to add yet another layer of new notation. So which one do you prefer?
I prefer matrices.
You prefer matrices? I do too. Okay, let's do the matrix one. For everybody who thinks, wait a minute, I don't like adding matrices to everything. I don't like this mathematical extra layer. That's fine. Do exactly what I told you before. Replace all of these by their Lorentz transforms, get this huge algebraic expression, do the math, and you will find as if you had never done the transformation in the first place. And then you've shown that it's invariant. Let's do it in a matrix one. Here are the Lorentz transforms for our big W's, yes? My claim is you can write these components, all 4 of them, as a matrix times your original components. I'm sure you understand this is going to be called the Lorentz matrix in a second. What would the matrix look like? Can you tell? No new physics, just recasting in matrix form what's written here. How about I write this omega 0, omega 1, omega 2, omega 3. And this one would then be omega 0 primed, omega 1 primed, omega 2 primed, omega 3 primed. What should be here in order that if you multiply this matrix by this thing, you'll get exactly these primed ones that are written here.
Have for the first row 1.
1.
Oh wait, yeah. Wait. Yeah.
How many omega zeros should be in our expression for omega 0 primed? Let me ask the question again. Our omega 0 primed, this one, contains omega 0. How many omega zeros does it have? 1?
Wait.
Gamma 1.
A gamma. There's gamma.
Oh yes, that's true. Yeah.
Right. The matrix multiplication tells you, oh, wait a minute, this one times that one covers exactly this part. How many omega 1s should be in your expression? Just tell me. All right. Oh, times gamma. There's still a gamma here. All right. How many omega 2s are in here? 0. And 3s? Okay, there you go. If you now do the matrix multiplication of the first row with this thing, get gamma times omega 0, that's this one, plus minus V over C times gamma omega 1, gives you that one, and 0 times these two. So this one is now exactly covered. How about the second row? How many omega 1s are in omega 1 prime?
Gamma.
Gamma. Okay, so where should I put this, the gamma?
Second row.
Alright, how many omega zeros are in?
Minus V.
Do you agree with this?
Yes.
Because minus V gamma times omega 0 is exactly this one. And gamma times omega 1 is exactly this one. How many omega 2s? 0. How many omega 3s? Still 0. Alright. How many omega zeros are in omega 2? 0. How many omega 1s are in omega?
0.
Oh, I say omega.
It's actually W.
Yeah, W, thank you. How many omega 2? When I say omega, I mean W, okay? How many W2s are in W2 prime? 1. So, what's the last one?
0.
0. And the final row?
0, 0, 0.
0, 0, oh,
0.
there you go. So apparently we can recast our Lorentz transforms in a matrix. This thing is called the Lorentz matrix. I mean, it's exactly the same information, it's just written in a different way. Yes. Yes. These Lorentz transforms that we wrote here are if the two observers are moving in x direction with respect to each other. Now, if they're not moving in x direction, then that means these do not hold. You have to write a similar version for different direction. That means also the matrix changes. So this matrix holds for observers moving in x direction with respect to each other. We're going to keep that for now. This is without any loss of generality, right? You can always, we saw that before here, you're free to rotate everything without changing anything. Remember that? So even if you find that things are not moving in x direction with respect to each other, that rotation that we saw that is completely allowed, that means you just rotate it back to your x direction and you can use this one again. So it's a good thing that this thing is also invariant on the rotations. That allows that trick to work. All right. Now, shorthand notation. There you go. This is shorthand. It just means this 4 vector, the one with the prime, is a matrix times your original 4 vector.
What's the symbol?
This is capital lambda.
Okay.
For L, for Lorentz. All right, now we've written everything in terms of a matrix. Here's my claim. Right, remember that we were doing this? We wanted to show that if you have this particular strange combination, then it's the same as if you have never made the transformation. This is the invariance, yes? That this expression with the primes is the same as without the primes. We have to prove that. Going to put some primes here. I've written this expression, this one here. It was shorthand for this long string here. And we're going to replace all of these capital W's and capital V's by the Lorentz matrix times the original ones. Here's the thing now. It's all correct. But in order to do this in somewhat succinct manner, I find that the best thing is to add another layer of notation. I wonder if that's the didactical way to go. Remember that I asked before, let's write it as a matrix. It's not untrue, but doing so I find, you know what, I have to add another layer of notation for the people who know the Einstein summation convention. And at some point I'm explaining more notation than I'm explaining physics. So is it okay if I take one step back? This is completely correct, but not use it in order to not have to put in another layer. Okay? So this is correct. Keep it somewhere in the back of your mind for later uses maybe, other courses, say general relativity. I'm going to take the original route. Okay? Is that okay?
Just for curiosity, what's the new notation?
The new notation is that this thing is written as yet another matrix. It's a Minkowski matrix times this is again shorthand for this. And the original idea that I had was to now replace this one, or this has primes, by this. Right, I've just replaced my primed 4 vectors for omega, excuse me, w and for v. Then replace these by this that we've now proven. And as a final step, you can then show that this new matrix just keeps track of these minus signs here. It's called the Minkowski matrix. And then prove that if you take these 2 Lorentz matrices and multiply them with this one, the one that keeps track of the minus sign here, that this thing itself is equal to that Minkowski matrix that keeps track of minuses. And this is a step that you do have to write out in full to show that that is the case. But once you've accepted that that is the case, you will find that all of this is replaced by this, which is exactly the original expression, but without the primes. And then you've proven that it's invariant. Now the reason that I'm not doing that, because when I was writing this out, I saw, wait a minute, but then I have to introduce the Minkowski matrix. It's all true. And if you're used to it, then this is by far the easiest method. But I find that there's this law of conservation of trouble here. Because in order to make this particular derivation very short, I have to explain an enormous amount of extra notation, which sort of mops up all the advantage that it had to go to this notation in the first place. So this is why I said at the beginning, there's a notation one of which the derivation is very quick. And there is one that takes more time to write out, but it's more mathematically clear what you're doing. And then we decided to do the matrix one, and now I'm deciding against it. So let's do the algebra one, after all, okay? How about I do it here? Now we now know what a Lorentz transform is. We now know how 4 vectors change. And let's go back to the claim that we're going to prove, namely that and let's make life very simple for us now. We're going to not look at the y and z directions. Okay. Now the claim was that this particular combination is the same as this without the primes. Remember that? That was this claim. For simplicity's sake, I'm not going to consider these latter 2 components. This is a claim that is the case. Now, I just erased it. Do you remember how this transforms? Omega 0 by Lorentz transform? Can somebody tell me how this changes?
Times W naught minus V over C W1.
This one, right?
Yeah.
Right. How about this one? How does this one change? Exactly. It's the same expression, but with all W's replaced by V's. V1. All right, so that takes care of. There you go. All right, but minus these 2. How does omega 1 prime, how does that transform? yeah, small v, okay. Okay, that's this one. And then there's this one. How does that one transform? Same expression. There you go. But now with all the w's replaced by v's. Be mindful that there's two v's in there now. One v is the difference between the relative velocity between the two observers, and there's the 4-vector v. I try to distinguish them by writing small and big for the two. Claim. If you write this out in full, you should get back this. If that is the case, we have proven this claim.
Are we missing the C's? Factor C it shouldn't be.
There's a c here, isn't it?
Shouldn't be minus b over c squared.
No. There is a minus v of v squared, but that's all in the gammons.
Because from that we have c on the other side. I mean, you have c dt dash is equals to comma c dt.
Oh, are you worried about this c here? Is that the one that you're missing? Okay. I don't want you to worry too much about that, because the 4-vector that contains the t's and the x's has this c defined within the 0 part. So it's a matter of definition. Okay, this is the big algebra expression that I said, right? How did I call it before? The law of conservation of trouble or something like that? I mean, it's much more clear what we're doing, because we don't have to add layer of new notation, but it takes more time to go through the algebra, but let's do it anyway. Well, one thing that I see here is that at least there's a gamma squared, these two. Let's write these out. Can somebody dictate what should happen if I multiply this by this? Already taking care of the gammas.
So it's w naught is going to be 0. Is it minus v over c w0 g1?
Well, you can just times that by 2.
By 2? No, not by 2, because no. Yeah, it's the other way around, right?
This is correct, right?
Yeah, that's yeah. And
Okay.
then plus v squared over c squared w1 v1.
Okay, that's this one. Somebody dictate?
Does the order matter in the multiplication of the...
No. No. They're just numbers. So 4 times 3 is 3 times 4 and such. Now we have to multiply this, right? Now I've already taken care of the gamma squared.
So it's not omega, it's w w1 v1 minus it's minus w the minus v w1 v0 what is that? Minus v w0 v1 plus v squared w0 v0.
Okay. Should have this. Alright. Just going through the algebra, law of conservation of trouble and such. I propose to collect all terms of equal products. So let's see if we can find all terms that multiply W0 times V0 from this. Which ones are they?
Wait, what are you doing with your gamma squared?
I haven't written it down yet, but it's there somewhere. sorry, what?
1 minus v squared.
And there's a gamma squared too, right? This gamma squared and that squared, gamma squared.
Right.
Okay. Are there any more of these combinations in there? I don't think so. Okay. Anything else? Well, let's go for everything that goes with
Yeah, so it's v of c squared and what else? Minus 1.
or minus, that's this one, right? Okay, oh, and a gamma squared, because both of them come with a gamma squared. Now there's more combinations. We also have this one.
That's
Minus v over c.
Yeah, and everything's going to be multiplied by gamma squared again, so let's take that out of the brackets.
And then minus
Plus v
Are you a minus or a plus? Which one is it?
plus.
it's
Oh, no,
plus.
Okay. Finally, I also have this one.
The same.
It's very much the same, isn't it? There you go. All right, let's clean up a little bit. This is just us doing the algebra. Remember that gamma was this. So what is this?
One over gamma.
1.
This is 1?
Right?
I have 1.
No. It's minus 1.
It's minus 1.
So yeah.
Wait a minute. W1, V1 with the minus sign. Is that what we were looking for? So it seems to be going the right way here. Huh. How about this? What is this? Yeah, that's your missing C. You were right. How about plus 1?
Aren't we missing c?
Yeah, there's a missing C. That's true. Made a mistake somewhere. I'm going to correct it in a second. Ignore the C's for a second. I will correct it for that in a moment. Made a mistake somewhere. Apart from the C, do you see that 1 minus V, ignoring C's for a second, times gamma squared, which is this thing, will give you plus 1?
Yeah.
Okay, good, because that means that we have a W0, V0 with a plus 1 in front, which is this. Alright? How about these two? Now, when I was writing this down, I could immediately tell, wait a minute, I forgot a C somewhere. Because this thing has no dimension, it's a number, and this is a V, it's meter per second, so I made a dimensionality mistake, some stupid algebraic mistake.
So the second line.
Yeah, well, I know exactly where it is, I will correct it for a second, but if we're just going to ignore the C's for a second, let's call them 1 for funsies, okay? What does this become?
0.
0, and how about this?
0.
Okay, so that means that these two combinations do not appear in the final expression. So ultimately, if you have gone through the math, you will have found that this is the case. That's this. Which is exactly your starting expression, but now without the primes. Agreed? So that means that my claim that I made here is indeed correct. We're not going to bother with the matrix notation here. My original claim was that this particular combination, 2, 4 vectors, combined in this particular combination is an invariant. If you do the Lorentz transforms on it, you get exactly the same result back. And here's the proof. So indeed, this particular combination is exactly the same as the ones with the primes. And that was the claim that I made. Now there was an issue with the C's. Okay? There's no physics issue here. It's just a stupid algebraic thing that I did. Can you tell what it is?
The Lorentz transform for the second one, that should have been like
somewhere over here?
yes, no, not there, but the one we have for the dt, it had the c in it.
Yes,
so
exactly. Yeah, that's the origin. Now, remember that at some point I said, well, the dt's have to be multiplied by a c in order to give them the same dimension, otherwise you cannot make this particular combination. Okay? So that means that the dt's have this extra c compared to the dx's. Now, in this particular case, with the dt's and the dx's, I had to add that extra c over there. In our general 4 vectors, capital W and V, I never had to make that assumption. So that means that using these Lorentz transforms with these C's, I don't have to add this extra dimensionality C. So this is why there's a C missing over there. Don't think too much of it. Is that clear to everybody? If not, let me repeat it because it is somewhat important. These dt's and dx's do not have the same dimension. So I was forced to add an extra c over there, some speed. Okay? The Lorentz transforms that we derived, in order to make the dimensionality come out right, had this extra c in there, this c, and that c. Okay? When I use the same Lorentz transforms on my capital W's and capital V's, I had no reason to add these extra c's in there. So that means that there's a c short over here. There's no issue in the mathematics, there's also no issue in the physics. It's really just that I applied this particular form of the Lorentz transform, including the extra c, where this extra c was not needed over there. So that means I have an extra c missing somewhere.
Is it the extra c kind of in the W?
Yeah, well, that's another way of putting it. I've absorbed the extra c in the W here, in the W zeros.
Yeah.
And if you try it out again, you will get exactly the missing c's everywhere, and everything will still be the same conclusion. So that's the issue. There's no physics difficulty here, or no mathematics difficulty. It's just I defined my capitals W and V's with the C's already defined in place. So that's the issue. Anyway. All right, long story, but here we are. Any combination of 2 4 vectors in this particular way will be invariant. Now, in a world where numbers change from observer to observer, people are very happy with invariance, because those are numbers that are not going to change from one observer to the next. So in relativity, we're all extremely happy if we find combinations of things that themselves are invariant. We have now found a particular combination. Every time that I have 2 4 vectors and I make this particular combination, then I know that even though these numbers apiece are different from one observer to the next, their combination is going to be the same. Now, can I erase it? How about I give you 2 4 vectors? Remember, we were building our way towards this relation. I'm going to give you a 4-vector. Question to you. Check for yourself that this is indeed going to be a 4-vector. We're going to write down right now. Okay? Question, is this a 4-vector? I see people nodding, I see people shaking their heads. So.
Is that C supposed to be in there?
Yes, there it is, supposed to be in there.
Is that
Because
X
I want
supposed to be
everything.
They're all the same dimension.
Yeah, they have to be the same dimensions.
Is that X supposed to be there? Which is the on the left side? Is that dx?
Yeah, but this is the shorthand notation for this thing.
Okay.
The question is this a 4-vector? I've put 4 numbers in a column. And the question is that a 4-vector? I told you, not every 4 numbers in a column makes a 4-vector.
You need to prove it with Lorentz.
Oh yes. Remember that we said that a 4-vector is by definition a thing that has a certain property, namely if it transforms under a Lorentz transform. So the question whether this is a 4-vector is really the question if I would write down this with a prime, it's exactly the same as if I had Lorentz transform this one. Now, I know how to Lorentz transform dt's. There you go. I also know how to Lorentz transform dx's. So again, is this a 4-vector, that thing? Does it change according to a Lorentz transform? Let me phrase it very clearly. How is this related to dt's and dx's without the primes?
Should be used.
Well, via Lorentz transform. Right? Yes.
It's maybe not the sign missing in the matrix.
A sign missing?
Yeah, like maybe like minus C.
No. There's a subtlety there that we don't have to be concerned with here, but if you would write down a mu downstairs, it would have an extra minus sign over here. But once I decided to skip that particular notation with the matrices, I'm also skipping that step.
Okay.
Did we talk about this before? That the dt's transform in this particular way? It follows a Lorentz transform. We also know that the dx's also follow Lorentz transform. So let me ask again, if you know that all these components transfer via Lorentz transform, does that make this a 4-vector? The answer is yes. In fact, it's the prime example of a 4-vector. I'm going to make another one. So this is a 4-vector, yes, because we know it transforms under a Lorentz transform. How about this one? Let me write down what I mean by this. It's exactly the thing that we had before, but now everything is divided by d tau. Question, is this a 4-vector? I've taken this one, and I've divided every component by d tau. Is that a 4-vector?
Speaking without knowledge, if it follows the rules of the matrices, but if it does, it's not.
I agree. But does it?
I guess.
If I transform to some other guy's coordinate frame, I know that dt will change according to a Lorentz transform. Dx will also change according to a Lorentz transform. The d taus, do those change from one observer to the next? I'll give everybody a second to look at the right-hand side whiteboard.
They should, right?
They should or they should not?
They should too.
I see people nodding their heads, I see some people.
It's the same towel we're using there.
It's this towel.
It should.
It should. Because the tau is invariant. That's our whole starting point of special relativity. So I've taken something that transforms on a Lorentz transform, that's this part. So this is a form factor. I have to divide it by something that does not change. So do you then see that the outcome will just change according to a Lorentz transform? Right? Dividing by a number that's the same for everybody will not change the invariance. So this is a 4 factor. How about this? I multiply everything by m. Mass of a particle. Is this a 4 factor?
Yeah.
Given that the mass is the same for all observers,
Then yes.
then this is also a 4 factor. Alright? Now this particular 4 factor, but that we've constructed from a prime example of a 4 factor, has a special name. It's called P mu. Maybe you can already tell why it's called P mu. You just write down what it is. It is P1. And it's by definition, it's this thing. Okay? So let me write down exactly what everything means. P0 is mc times dt d tau. That's this one. Then there's P1, which is m times dx d tau. P2 is m times dy d tau. And finally, P3 is m times dz d tau. This is just a definition. We've already said that this is a 4 factor. Now, in a moment, we will see what the physical interpretation is of this thing. But before we do that, let's apply this theorem that we have here. If you take two 4 vectors, you multiply them with each other, in this particular combination, you will get something that is invariant for all. We've seen that this is a 4 vector. If we multiply this with itself, you multiply two 4 vectors. If you will, what I'm doing now is I'm taking capital W as P. I'm also taking V as P. Two 4 vectors multiply with each other. We've shown that's always going to be invariant. Let's see what we get. I'm going to take these two, multiply with each other in this combination. P0 squared minus P1 squared minus P2 squared minus P3 squared. Is this invariant? Checking question? Yes, it is. Because each of them is a 4 vector, and this combination of 4 vectors we just proven is always going to be invariant, so this is going to be invariant. What will come out of here is some number, and that number is going to be the same for all observers, even though their p's are going to be different. Let's calculate what that number is. P0. That's this thing. M squared. Just plugged in what the individual components are. Claim. The number that will come out here is minus m squared c squared. Take a second maybe to see if you can tell why this is.
missing squared in the x with the m.
Yes, thank you.
Especially derived by tau, the other times the x, the y, z are the 0.
Why would it be 0?
Is there no tau? No? Oh wait, no.
It has to do with the tau though. You remember the formula for time dilation?
Yes.
Can you tell me what it was?
T equals gamma proper time.
Yeah.
So dt equals gamma times d tau.
Yes.
But it's still the same d tau, right?
It's the same d tau still. But because this d tau that I've divided everything here was that d tau, and when we did the derivation of the time dilation, we got this relation with this d tau. So it's all the same d tau. Hey, but doesn't that mean that 1 over d tau is gamma 1 over dt? Just following the math where it leads us? But doesn't that allow us to rewrite every 1 over d tau here by gamma 1 over dt?
Yeah, so we get.
I mean, we've derived this before, so we know that this holds. Can you tell me what will come out here?
So that's going to be gamma squared, yes. Gamma squared
Yes.
minus d.
Isn't there anything forming here still? Let's see, if
Wait,
I
what should
replace
be
1 over d tau here by gamma times 1 over dt, I get a gamma squared here because of this square, and I get dt over dt, which is 1.
Yeah.
So that's this.
Yeah.
How about there? How about what happens over here?
Yes, so nothing should be following, right?
Sorry?
Nothing should be
No,
following.
no, no. This is complete.
Yeah, okay.
It's a trick question.
Okay, yeah, I was just thinking.
Okay. How about this? I replace my 1 over d tau by gamma times 1 over dt.
So it's gamma squared
Here gamma squared,
times.
taking it.
Wait, is that correct? Sorry. No.
Yeah, it should be.
Oh, yeah, it should be. Sorry, yeah, because it's inside. Yeah. Times
Yes.
squared. Yes.
How about this is
dx then, right?
dx dt. Dx dt.
Yeah. So it,
Velocity.
yeah.
That's the velocity in x direction. Whose velocity is this, by the way? It's a question that we encountered before.
Oh, it's the relative between the two observers, right?
Yes, exactly.
The two four vectors.
Yes, we made a point of that before. That
Yeah.
dx dt is the relative velocity between me and him and,
Yeah.
and his water bottle and exploding firecrackers and such. And the same here. There you go. Here's the velocity in in x direction, velocity in y direction, velocity in z direction. Let's group everything together.
You forgot.
Are you missing gammas?
Y and Z.
No, I'm missing gammas. Oh, yeah, sure. Here's a gamma too, and here's a gamma. And from here to, so I've used time dilation to go from here to here. And I put all the v's inside this one overall bracket. Yes, and there's an m squared, thank you. Now, if I have a certain amount of velocity in x direction and in y direction and in z direction, and I square them all and I add them together, that's Pythagoras theorem, isn't it? For the velocity. So I propose to call this the velocity squared.
Sure. Yeah, okay.
I think I'm hearing the gasps of understanding, because this v is now the v in any direction, the total v, total velocity. Can you now see that this will equal that? So close. Yes, there's a square here. I'm constantly forgetting my squares, I don't know why. This is just algebra from here to here.
What's happened?
What I did here, I took an m squared c squared out.
Okay.
Yeah. There's a gamma squared that I can also take out of the brackets. What you can also do is just multiply these brackets out. M squared c squared times 1 times this gamma gives you this.
Yes.
And this one times this will give you this.
Yes.
So algebraically the same.
Oh, and that's one over gamma squared.
Yeah, this is 1 over gamma
So
squared.
then that becomes 1. Where does your minus go then?
I think you just made a mistake. Or maybe I just guessed that it was going to be that. Not smuggling here. This is the correct expression. So there we go. All right. So we have that. Well, that was a claim that we were going to make, right? We said that any combination of two 4 vectors, this particular combination, will give you a number that's going to be the same for all, isn't it? Didn't we prove that explicitly before? Now, what we found, if you actually do the math, that number that's going to be the same for everybody is going to be c squared times m squared. Okay, so we have that. Yes?
If you're using light, which doesn't have mass,
And then you cannot use this.
then what do you use? Oh, but it doesn't. Okay.
The reason is somewhat outside of the main topic here, but if you use light, then you know that this amount here is exactly equal to c squared times dt squared, or in other words, d tau for light is 0. So you cannot divide it here by d tau. For light it will be 0. I would have made it mathematically not a fine step. So you cannot use this for light. Okay, now, what we've done now, we've proven before that any combination of 4 vectors in this way will give you a number that's going to be the same for all. For this particular 4 vector that we constructed, we first showed that it was actually a 4 vector. So we noticed that the number should come out should be the same for all. We've calculated what that number is, m squared times c squared. Can you already see something like this happening here? The last thing that we have to do is convince ourselves what these numbers are. I mean, I just constructed the 4 vector. I just took the prime example of a 4 vector, multiplied it with some m's and c's, and divided by d taus and such. And then I got these things. My claim is that these are momentum. It's not coincidence that I called them P. And that this one is the energy over C. Well, I haven't proven that that is the case. So if that is the case, that this indeed is energy over C, and this indeed is momentum in x direction, momentum in y direction, momentum in z direction, and we know that this particular combination should give you m squared times c squared, we're already sort of here, aren't we? Because the p-zeros, given that that has something to do with energy, will give you energy squared. The p1, p2, p3 are going to give you momentum squared. And everything added together should give you m squared, c squared. All in all, will give you that relation here. So the only thing for us to prove is that this is indeed energy and this is indeed momentum. Once we have that, we're done. Any suggestions at this point, maybe? What is momentum in classical mechanics?
Mass times velocity.
Mass times velocity. Well, it's sort of here. Mass times, well, is it velocity? Because it says dx over d tau, and velocity will be x over dt.
Well, the units make sense. But
Sorry?
the units are kind of correct.
The units are absolutely correct, yes. And it sort of gives you already the same interpretation, because it says amount of space divided by amount of time, which sort of gives you a velocity, times m gives you a momentum. But here's the rub. Dx is my amount of time, the moving observer, and d tau is the guy who's not moving. So I'm dividing somebody's distance by somebody else's time. So sort of like a bastard object.
Can't you then write that other person's time in terms of your time?
Okay, how would I do that? The time dilation. In fact, we've already used it before. 1 over d tau is gamma times 1 over dt. Let's do it here. That will give you gamma times m dx dt. Agreed? Yeah. I've replaced 1 over d tau using a time dilation formula as gamma 1 over dt. And now we have mass times an actual velocity. So it gives us gamma times mv. In x direction. And in very much the same way, this is gamma times vy, and this is gamma times mvz. Now, does it look like a momentum to you? It's a mass times a velocity, so classically it's a momentum. It's just there's an additional gamma there. So it's momentum-like. It's just you have an extra gamma.
So it's, what is it then? Sort of relativistic momentum then?
This is what they call a relativistic momentum. Yeah.
That's pretty cool.
And what you see, it's really just the normal momentum, Newtonian momentum, times gamma. Now, if you're not moving too fast.
Right, of course, this is based on velocity. So it's based on your... No, sorry.
No, go ahead.
Yeah, no, just because it has the velocity term in there.
Yes.
That means that it's going to be... it's going to depend on your time, your velocity relative to something else.
Yes.
So different people are going to see your momentum different.
Yes.
Right? So
Yes.
That's why you add the gamma.
Well, I didn't add it. It just came out of the calculation. But yeah,
Yeah.
I mean, but this is the physical interpretation.
Yeah.
So what we have here now is a momentum. And if you're not moving too fast, in other words, when gamma is, for all practical purposes, 1, you just get the classical momentum, your Newtonian momentum, right? So apparently, in special relativity, you automatically get this new momentum thing that looks like the momentum that you're used to. It's just small differences at the moment that you're moving very fast. This conclusion was inescapable. If you think, well, you just constructed your original 4 vector in such a way that this thing came out, I had no choice. If I didn't wanted to have gotten a classical momentum out, I would have had to divide by dt. Agreed? The gamma got in there because it divided by d tau. Now, if I would have divided by dt, I would have gotten rid of this gamma here, but then all of this would not have hold. Why? Do you remember? I divided by something that itself was invariant, otherwise I could not use my 4 momentum trick. Take a moment to appreciate this, please. I started with this thing, well, there was a 4 vector. I said I'm going to construct a new 4 vector out of this. In order to turn this into a new 4 vector, I had no choice but to divide it by d tau. I was not allowed to divide it by dt, because d taus are invariant. In order not to spoil the 4 vectorness of this thing, I was not allowed to divide by dt's. I had no choice but to divide by d tau. Now, I'm perfectly allowed to construct a new thing, dx mu over dt. I would have gotten 4 numbers in a column, but it would not have been a 4 vector. And this trick I would have not been allowed to use, because this was only proven for 4 vectors. That's the reason. Yes?
But you could use dt gamma instead of the tau?
Yes, but that is tau, of course, d tau. So what I'm trying to give you an argument for here now is that that all of this was inescapably a gamma built in. That's the only way to make this into a new 4 vector. So me getting this new momentum out have very little to do with personal choices. It was the only way that I could turn my prime example of a 4 vector into a new 4 vector, to retain its 4 vectorness. But I'm very happy. I mean, what I get here is something that I already knew, namely classical momentum, but now in full 4 vector notation. And 4 vectors are nice things. So yes, this is what we call relativistic momentum. And it just goes over into classical momentum if you're not moving too fast. Now this thing. My claim is this is energy over c. It's maybe more difficult to see. Or maybe it isn't. Maybe it's even easier.
So we can rewrite dt over d tau as gamma, maybe.
Something like this?
Yes.
Because the 1 over d tau has now become a 1 over dt. That cancels the 1 over dt here, so this is what you get. Claim, this is energy over c. How can you tell? There's at least 2 ways. What is the dimension of MC gamma?
Sorry?
What's the dimension, the unit? MC gamma. My claim is it's an energy over velocity. Kilogram meter per second. What's the dimension of gamma? It has no dimension. Dimension unity. All right. What's the dimension of energy, generally speaking?
Joules.
Sure, but that's a short notation for some other stuff.
That's kilogram.
What's it again? Meter second squared. Meter squared second squared.
One way of looking at it is this. Potential energy would be force times distance. A force is mass times acceleration, so kilogram meter per second squared. In order to turn that into an energy, potential energy, you have to multiply it with distance. So it gives you another meter. This is in total. My claim was, this is energy over c. Can you tell that that's the case just by dimensions alone?
Yes.
Okay. So E over c. I haven't quite proven this because I've just shown by dimensional analysis that it's an energy divided by a velocity. It might have been velocity v. So it's really just a happy guess that the velocity that you need in the denominator is the speed of light. So let's give a more strict argument here. I'm going to take the gamma here, which you know is this thing, this gamma. How's your Taylor series? Man, don't you love theoretical physics?
Let's go.
For small v's, a Taylor series will tell you that this is this. I don't feel the inclination to work that out, but you know how to do Taylor series, yes? So were you able to figure out that this is true from there to there?
At some point, after a long time, trying. Yeah.
Okay, let's accept it as fact. It is. It's not that hard. What you have to do is take the first derivative of this thing, substitute v is 0 in there, multiply everything with v. Anyway, this is what you will get out. All right, here's the claim again. MC gamma divided by should be this is my claim, energy over C, yes? That's my claim. By dimensional analysis, we saw that it's probably something like that-ish. MC. And for the gamma, I'm going to use my Taylor series here. By the way, there is a loss sign here, excuse me. Doesn't matter for my argument, by the way. You get this. I haven't done anything, by the way. I've just rewritten my gamma in a equivalent mathematical expression. Work out the brackets. MC plus 1/2 mv squared so I've taken this expression, Taylor series it, and I get this. Now I'm not going to bother with the MC. You can. But you know from classical mechanics that you can add constants to energies without changing the physics, yes? Forces are defined by the changes in energy. So adding constants to energy will not change your physics. So you don't have to worry about this thing. You can add 514 to this and still get the same physics. But this part is interesting. 1/2 mv squared. That's a kinetic energy, isn't it?
Is it only kinetic energy that we have in this case, though?
No, because the Taylor series has more terms.
Okay.
But for my argument, I cut my Taylor series off to only one term to show you that there's a kinetic energy in there.
So if you would add more terms, how would that final thing look different then?
Oh, geez. V over C to the 4th. And there's a numerical factor in front. I'm guessing there's 1 over 6, something like that. You get extra terms.
Okay. So how would that change the line below that then?
You would just get an extra term, namely this times MC.
Yeah. Oh, okay.
So there's a multiple of terms in there, right? The Taylor series is exact at the moment that you take all infinite terms. For my argument, I'm only going to use this particular term here, this one, because what I want to show you is that this is energy over C. And that was my claim. There's energy over C. We have a complete rounded off argument now. We saw by dimensional analysis that this thing is an energy over a velocity. The question was just, which velocity is that? And our Taylor series told us, oh, it's 1 over C.
Is that an exact argument or an approximation?
No, it's an exact argument. I mean, of course I made an approximation here. One step back. We show by dimensional analysis that the P0 has the dimension of an energy over a velocity. Okay? But we have two velocities in our story, namely C and relative velocity V. And the question was, which of the two is it? And what I've done now is, well, I can take my Taylor series, I can just read off that it was C all along. And that completes the argument. It was energy over a velocity. Taylor series tells us that that velocity happens to be the speed of light. And that's all there is to it.
So, whose energy is this then?
It's the energy, it's a guy looking at some phenomenon, moving along with the speed v with respect to that phenomenon, and him looking at the energy of that thing. It's me looking at the water bottle's energy as I move along.
Yeah, okay.
Yes?
Isn't it kind of weird that this gives us a non-relativistic formula for energy?
It doesn't, because I've cut it off here. If you take all the other terms into account, it is relativistic. Again, the reason that I cut off my Taylor series is because I only need one term to show that the missing velocity is the speed of light. Long story short, this really is energy over C.
Is energy also relative then?
Yes. That was also the case in Newtonian mechanics without special relativity. Right? What is your kinetic energy compared to me?
Well, 0.
0, okay. What is it now?
Well,
You have relative velocity, so all of a sudden my 1/2 mv squared for you is going to be a different number. So even in classical mechanics, energy was already relativistic.
Relativistic or relative, right? Not relative.
Relative. Not relativistic in the sense that it obeys
Did
special relativity.
Newton realize that?
Yes.
Okay.
Again, this is the reason why he came up with Newton's first law. So he knew in what observer frames he could use his formula. Now, he was a smart guy. I mean, there was a reason he put in the first law. Wow, long story short, this is energy over c and it's squared. These three together give you the total momentum, relativistic momentum squared. Right? This is just relativistic momentum in three directions. In total, gives you relativistic momentum squared. And what comes out? That should give you this. Here's a relationship between masses, energies, and momenta. Agreed? Now what if you take the p to the other side and multiply everything with c squared? You get exactly this. And I promise you I was going to show that that is the case. Man, that was a long story, wasn't it? Are you convinced though? Have you noted that in order to get this equation, ultimately the only thing I've used is this equation? Just recapping. I use this equation, showed that Lorentz transforms were built into there. Then I showed if you have two 4 vectors and they obey the Lorentz transforms, this combination, where is it? This combination of two 4 vectors is going to be invariant. Then I constructed the 4 vector from my starting point, added some m's into there, but that's all that I did. Then I showed that the separate components necessarily, without any question, I had no choice to do it this way, what gave us momenta and gave us energies. And because I've already proved that this total combination should give you an invariant, I calculated the invariant and I got this equation. All of this is all just this, and the rest was math. That was the claim that I made, that all special relativity was in there. No thought experiments, no lights, no mirrors, no trains, no tubes with photons flying from one side to the other. I mean, it's a fine derivation, but this is the cleanest that you have, because it's really just this expression, and math.
How do you get this expression?
Well, that's just our starting point, our axiom of nature.
Well, from where do we derive it?
How do you notice that relation?
Well, this is a very good question. How do you know that f equals n times a?
They told me.
Yeah, okay.
And I believe it.
No, it's a good question though, but you cannot derive anything from scratch, from literally nothing. You have to have a starting point. Now, in the thought experiment way, what people take as starting point is, oh, the speed of light has to be the same for everybody, do some thought experiments, and then you get the Lorentz transforms and such. The only thing I did was, well, forget about the speed of light being the same for everybody. Let's take this as a starting point. It's much more abstract, I agree. Speed of light being constant or being the same for everybody is a statement that you can easily envision physically. This is much more difficult to envision. But I mean, it is a new starting point. How about this? In order to make the full circle, the usual starting point is speed of light is the same for everybody. I haven't said anything about light. There's no light in my experiment. There is a velocity that happens to be the speed of light, but there's no actual light in there. How about to make full circle with the usual derivation of special relativity? We now prove that speed of light is the same for everybody.
Sounds good.
Yeah. Because then we have connected everything to everything, okay? Then we've really shown that the derivation that you've seen before, that had that as a starting point, is really just the same as this. Because what Chris did with you was take that as a starting point, the speed of light being the same for all observers, and then derived these equations and such. What I've done now, I've started here, and I'm now going to derive Chris's starting point, so we have full circle now. His starting point leads to mine, and my starting point leads to his. Unfortunately, this is an easy step to make. Can I erase this? Nah, not relativity.
That's so simple.
So let's call this the let's connect to Chris part of the lecture. We're going to do the following. We're going to see something move past. Let's take the famous water bottle again, okay? Don't do it in practice, but suppose that you throw this through space. Don't do it. Okay? Throw this thing through space. And I happen to be walking along and I see a water bottle flying by all of a sudden, and I measure how fast the water bottle is flying compared to me. All right? Now one of you is also walking by. Suppose the two of us are walking here. One of us is going a little bit faster than me maybe, and both of us see a water bottle flying by. I can measure how fast the water bottle is flying with respect to me. What I just do is see how many seconds it takes for that thing to fly 1 meter or something like that. The other guy can do the same thing. Now he will typically get a different answer than me. Not even because of special relativity, even in Newtonian mechanics it will be the case, yes? If I walk with 1 meter per second and the bottle comes flying by with 7 meters per second relative to the ground, then my velocity of the bottle is going to be 6 meters per second. If the other guy is walking twice as fast as me, he will see 5 meters per second for the water bottle. Oh, excuse me, 5? Walk here. Yeah, if he happens to be walking in a different direction. I walk here 1 meter per second, the water bottle comes flying by 6 meters per second, both with respect to the ground. Relative velocity between me and the water bottle is 5. The other guy is walking with 2 meters per second squared, the water bottle comes flying by with 6. His relative velocity is 4 meters per second. Okay? So already in classical mechanics, Newtonian mechanics, velocities are not invariant. They're different from one observer to the next. But we're going to do it special relativistically. So let's make me the primed coordinate guy. Okay? And the speed of the water bottle I'm going to call u. I'm not going to call it v because I'm going to reserve v for the relative velocity between me and the other guy. And this is u, the velocity of the water bottle. Okay, classical mechanics. How do you calculate something's velocity?
Distance of position.
Of course. I just measure how many meters the thing flies in how many seconds, both measured by me. dx over dt. But remember, there was also some other guy, also walking, different velocity than me, also sees the water bottle flying by. So that's the primed coordinate. He also sees the velocity of the water bottle. In my numerical example, a second ago was 4 meters per second, I think that it was. I'm going to call how fast he sees the bottle flying by u primed. What's the expression? Well, how many meters he sees the bottle flying by, dx primed, divided by how many seconds that takes for him, dt primed. If this were classical mechanics, this dt will be dt primed. It isn't. It's relativity, and dt's are not, one guy's dt is not the other guy's dt.
So dt prime is then, no, wait.
You know the funny thing is, Kai, I have the impression that I can see what you're thinking, and I see you correcting yourself. Can I guess what you were thinking?
Yeah, go for it.
Okay. You were probably thinking, wait a minute, but this dt is gamma times some other guy's dt, and then you thought, wait a minute, but time dilation only works if one of the guys is standing still with respect to the water bottle, and none of them are. I have to use these. Thank you. This was what you were thinking?
Yeah.
Okay, good, because that is good. Remember, time dilation, that one guy's dt is gamma times the other guy's dt, only works if one of the guys is standing still with respect to, in this case, a flying water bottle. But neither of us are, and we made a point before that for the general case you have to use these. But that's fine. I mean, I know how to write my dx primed in my dx's. In fact, we can do this for the numerator and the denominator. So what is the numerator here?
This
Gamma dx over v minus v dt.
Yes? Okay. And numerator? So, excuse me, denominator?
That's
Then you have to divide
divide by c.
What is
Yeah, that's true. Okay, so there's a 1 over c there, right? Yeah. People who know me from particle physics know that I tend to mess up my c's, just as I did before.
Why is it 1 over c?
Why?
This is probably one of my messing up of c's. Let's see.
Yeah, it should be just c, right?
It should be just
1 over c here.
Yeah, but the one inside.
Yeah, what about that?
This.
You have 1 over c dt.
Oh, so it should be this?
That one, yes.
That is correct. This is correct, I think, now, isn't it?
Yeah.
Okay, good. Let me continue on black for the viewers at home. Okay, well, 1 over c in total will just be 1 over c will just give you a c. The gammas drop out. Then I get dx minus v dt. And below I get c dt minus v over c dx. Agreed? Just doing the algebra here.
Yeah.
Alright, do some more algebra because I can sort of see some use in there. Remember, this velocity of the flying bottle as seen by one guy, but by the Lorentz transforms, I was sort of able to write everything in terms of my coordinates. Now, if I can make a dx dt somewhere in this combination, I can replace it by my u. And, well, it's sort of already there, isn't it? How about I take dt out in the numerator? Then I get dx dt minus v. Is that correct? And suppose I also take a dt out in the denominator. I get c minus v over c dx dt. So you agreeing with me so far? Just algebra. The dt's drop out again. I get c. What do I call dx dt? U. Great. Minus v. Nothing to do there.
Which v is that?
This is the v, the relative velocity between the two observers. Yeah. U is how fast I see the water bottle moving, and u prime is how fast the other guy sees the water bottle moving. I see a c here minus v over c. What is the xct here? Okay, good. No, just checking. But people don't say, oh, the xdt is probably v. No, 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 no. Be very clear what things mean. V means relative velocity between the two observers. The xct is u, the velocity that one of the observers sees the water bottle flying. Okay, so apparently what we have here is a rule that tells me that if I know how fast I see the water bottle moving, and I see how fast you and I are moving with respect to each other, I can calculate how fast the other guy sees the water bottle flying. Agreed? What would this be in Newtonian physics, by the way? I see a water bottle flying with velocity u. You and I are moving with respect to each other with velocity v. How fast is the water bottle flying with respect to the other guy? I make it very explicit here. I'm walking here. Boom, 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 boom. Water bottle comes flying by. I see that it goes as 5 meters per second. Some guy is walking 1 meter per second faster than me. He also looks at the water bottle. How fast is the thing flying with respect to him? 4 meters per second. In other words, how fast I see the thing flying minus our relative velocity, yes? Well, that's
So
this part. And apparently, in special relativity, using Lorentz transforms, you have to divide it by something. Now, the thing that you have to divide it with is typically very close to unity. Can you see that?
What is unity?
Let's make it explicit. There's a C here, there's a C here. They cancel each other out at the cost of another C there. Can you see that if the water bottle is flying very slowly, or slow compared to the speed of light, and you and I are moving very slowly with respect to each other, then 1 minus this thing is very close to 1, and you just get back your Newtonian rule. So apparently, we get the same rule as in Newtonian physics, plus a little difference. And the difference only appears the moment that you're moving very fast, or the water bottle is moving very fast. This is the Einstein velocity rule. He derived this in 1905. You cannot just simply Newtonianly, that's the word, subtract each other's velocities and then get the right answer. That doesn't work anymore in relativity. You have a denominator now that messes up the stuff. This is what comes out. That was not my claim. My claim was, suppose that somebody sees something moving with the speed of light. We have now a water bottle flying by with the speed of light. Okay, this rule is general, should also hold for water bottles to go with the speed of light. So this is the general rule, but here's a special case. Suppose that I see the water bottle flying with the speed of light. How do I put that into my formula?
So
V equals C.
Not V
no,
equals C.
U, right?
No, U equals
Yes, because V is the velocity, the relative velocity between the two observers, and we're not, both don't have the speed of light.
Right.
Now I see the water bottle flying with the speed of light, so U is going to be C. How fast I see the water bottle flying is going to be C. Let's plug it into our formula. C minus V, right? I'm just going to put all my U's equal to C. Agreed still? Just check for yourself that this is the case, yes? Replace all U's by C's. Let's see how fast the other guy sees the water bottle flying now. There's a C and a C squared here, so they drop out. Like this. This is just algebra.
How? What would?
I took this C in front of the fraction.
Yeah.
So that makes this 1 and that makes this V over C.
Oh shit.
That's amazing.
These drop out. Gives you C. It doesn't matter how fast you and I are moving with respect to each other. Does the number for V matter?
Well, no, doesn't. Right?
No, because it drops out regardless of what the number for V is. So we have a very special rule now here. We found that in special relativity, if one guy sees something moving with C, then the other guy does as well, regardless how fast they themselves are moving. Appreciate this fact for a moment.
That's really cool.
That is, yeah, it's really cool, but it's also very weird, because that means, suppose here's a flying water bottle and it goes with C, okay? And then you come running next to me, and you and I are moving with you're moving with respect to me with, say, 80% of light speed. Do you think, well, I'm going, that water bottle is going not as fast compared to you as to me, right? Because you're gaining in on it with 80% of the speed of light. Nope. Relativity tells you, no, you still see the C. This is Chris's starting point. So we've made full circle now.
Yeah, I remember he started with something. It was like this spaceship moving with. No. There was a spaceship moving with like 50% speed of light, which then would send out a beam of light.
No, there was like a star, and there was like two spaceships going at the star.
Also that one, he did that one.
Okay.
Yeah. And so yeah, from that he kind of.
He did a good job. I mean, he took this as a starting point and then derived other stuff. We just went the other way. We started here. I'm sure that Chris told you that this combination is invariant. And I'm sure that he derived it at some point. I took it as a starting point. I derived his starting point. Yes?
It's probably a stupid question, but then, okay, now you and Chai are also traveling at C, so B is also C. But then you get U prime is equal to 0. How do you interpret that?
Wait a minute. So he and I are both moving with C?
Yeah,
So
but you
B
see C as C in any frame, so he still travels at C even though you're traveling at
So
C.
that means that if I'm traveling with the speed of light and he's traveling next to me with the speed of light, then you would think, oh, that means that the both of us are moving just along each other, right? No, he looks at me and I see him with the speed of light. He sees me with the speed of light.
Yeah, but in U prime it says 0, right?
Oh,
That's
no. What would V be if both of us are moving with the speed of light? No, it wouldn't.
We can not be
oh,
zero.
so you're not supposed to take in the relative, well, the fact that C is C in any frame. You're supposed to say, oh, both of you are at C, so your relative velocity is still 0. Is that how you do it?
You're going to hate this answer, but the question is ill-posed. And you're assuming that either he or I or both of us are moving at the speed of light. Okay, but and then if you look at this, then strange things seem to happen all of a sudden. But here's the thing: at the moment that both of us or one of us move the speed of light, then d tau is going to be 0. Okay, but we built up everything assuming that d tau itself is not 0 because we've been dividing through d tau all this time. So that means that your starting point of your situation, your question, does not agree with our initial assumptions. This formula does not hold for things that themselves move at the speed of light. Observers moving with the speed of light. They can be looking at something that goes with the speed of light. So we're dividing by 0. This is the reason why your question does not fit our initial conditions. Yes?
Sorry, how is tau going to be 0 in the case of C?
If something moves at the speed of light, what it says here, c times dt, is exactly the amount of space something that moves at the speed of light would have covered. In other words, this is exactly equal to the amount of space. So you take the amount of space minus the amount of space traveled, gives you 0. So, long story short, if something moves at the speed of light, d tau is 0, and all the mathematical steps where we've been dividing through d tau would not have been allowed, and all of this conclusion would not hold. That leaves us with the final question. Is Chai allowed to move at the speed of light? Why not? Yeah, but how can you tell from everything that we've written down? You're right, it's a correct. The moment that something has mass, it cannot move at the speed of light. How can we tell? I mean, my claim was everything in special relativity follows from this, and everything so far has. But this claim we have not shown yet. That sort of answers your question why we cannot use this formula to when one of us is moving at the speed of light, because we have mass. Fortunately, this too is only a small step away. What's the expression for energy?
What energy?
Well, the expression how much energy you see. Chai is moving aside me, and I want to know what his energy is. That's that expression. I take his mass, m, multiply with c to the 4th. I measure his momentum, gives me a number, make this combination, I know how many joules he has, as seen by me. So I get this. Do you remember what P was? A relativistic momentum, what the expression was?
Gamma.
Right? The relativistic momentum, P was gamma mv. Squared gives you this. Oh, and I'm missing the c squared. This c squared. Agreed? Well, now we have something beautiful because we now have E expressed in V's and N's. Over here we had E expressed in M's and P's. I've now expressed in velocities and masses. And you can just do your standard first year algebra. Did you say, well, that means that E is just a square root of this thing. But you can already sort of see what's going to happen. Right? Because I see an m squared, another m squared with the square root will give you just an m. There's a gamma here, there's a c to the fourth, there's a c squared. If you go through the algebra, you will find this expression. The square root of this thing is just that thing. No trickery going on, just doing the algebra. If you don't believe me, take this thing, square it, put it in here, and see that gives you this. Or do you really want to see where this comes from? Do you believe me when I tell you? You believe me? Okay.
I get where the v squared goes.
Well, there's a gamma squared here, and there's a v squared and a c squared somewhere. You can divide the c squared out, so ultimately you will make another 1 minus v squared c squared.
Oh, which then cancels the gamma.
Yes, and you will only retain one gamma.
Right. Okay.
Anyway, so just go through the algebra, you will see this. Now you know what gamma is, right? mc squared, 1 minus v over c squared. So what we have here is really just this expression rewritten in a different form. Which one you use depends on your situation at hand. This one is handy if you happen to be in an experiment where you measure momenta. This one is handy if you happen to be in an experiment where you measure velocities. Physicists usually use this one because momentum is conserved. So it's a much more easy to measure thing than velocity is. But I mean, it's the same expression. Hey, what happens if something is not moving with respect to me? I'm looking at Chai again. So you keep on, you and your water bottle are the prime example all the time. I want to know his energy and measure how much his mass is. We're standing still relative to each other. What is our V? 0. So what does this give you? If V is 0. So that. MC squared. E equals mc squared at the moment that we're not moving with respect to each other. Now you all know this formula, but now you've seen it derived from our starting point there. Here's your claim. But wait, can't you just absorb the gamma in M?
It's not like a claim.
No, this is true. I'm sorry. No, it sounds too harsh when I say it like that. But you made this comment before, and that's again a misconception that I would really like you not to forget about. There's a school of thought that says, well, you can absorb the gamma into the M, so you get this new M that is defined as the original M times gamma, and then this new M, this will increase as the thing speeds up, because gamma becomes bigger and bigger and bigger at the moment that things go faster. Then this new mass, defined as the old mass times gamma, increases. This is where the term relativistic mass comes from, that the amount of kilos is different depending on how fast things are moving. It's wrong. It's mathematically true, but it's physically wrong. Here's an example. I take Chai, or his water bottle. I take your water bottle, okay? And I hang it up some piece of rope here. Okay, so feels gravity. It has a certain mass. Let's suppose that it's 1 kilo, 1 liter of water. Now, let's suppose that the amount of newtons of gravity that the thing feels, well, 1 times 9.81 meter per second squared, let's round it up, say it's 10 newtons. Let's suppose I set up my experiment in such a way that the rope will break at the moment that it is 12 newtons. The rope can only handle 12 newtons of weight. The thing is hanging over here. And I look at it and I say, well, the thing has a mass of 1 kilo, so that means times 9.81, that gives us about 10 newtons. In other words, that's less than the 12 newtons that the rope can handle, it will not break. I have the same situation, thing is hanging here, I start running past this thing. Then I say, but look, relativistic mass then tells me that the mass of the thing will increase, well, all of a sudden if it moves fast enough, will not be 1 kilo, but 20 kilos. And as a result, the amount of newtons will be 200 newtons, which is more than 12, and now the rope will break. So which one is it? Will the rope break or will it? Or won't it? Well, do you agree with me that the amount of breakiness of the rope will not depend on how fast I'm moving past? Do you agree with that?
Yeah.
This is very different from cases where going from one observer to the other will make some numbers change. Because there's always something else that compensates for the missing number. If you go so fast that the amount of time changes because of time dilation, the difference will be mopped up by the amount of space. But there's nothing here in this particular setup that will mop up my extra amount of mass. Very clearly put, you cannot have a situation where one observer sees a thing break and the other one does not.
Oh, that's like with the rhino.
Rhino.
The rhino.
The what?
Yeah, Chris had this. There was this PBL task in the relativity course where there was like this rhino was executed under a guillotine.
Okay.
And his final wish was to go under the guillotine really fast. So from one frame of reference, he would be like
Lawrence contracted?
yeah, exactly. So then the blades would fall basically not on him, and the other frame of reference they wouldn't fall simultaneously.
Yeah.
And so like the question was what would actually happen, because he can't
Oh,
both die and not die.
No, exactly,
From
exactly.
different
Now in this
perspectives.
particular case, so what was the solution? Do you remember?
Well, the first thing I just said is what the solution was. So
Okay.
he wouldn't die basically, because
Okay.
in one case one blade would fall first, and then the other one when he would pass, and the
Yes,
other one he
exactly.
would contract.
Here's what it meant. At the moment that you see one number change when you go to one observer to the next, there's some other number that changes accordingly so that their total combination will be the same. In this particular case, length was shortened of the rhino, but the simultaneity has also changed in such a way that the net effect of these two effects is the same.
Yeah.
You cannot think of anything in this particular example with the flying water bottle or the water bottle hanging on a rope that is going to compensate for not breaking. Not even a Lorentz contraction, because the rope is perpendicular to the motion. So nothing will happen to the rope. So do you see that the idea that mass, the actual amount of kilos increases is simply not correct? Now it so happens that in this particular case it looks as if you can always do this. Here's one final example and then I will continue with the actual point. Remember that we talked before that you can apply special relativity to accelerating objects? Right? It's a misunderstanding that you can't, but you can. Now if you want to calculate an acceleration, you use Newton's second law, yes? Now this one does not hold anymore in special relativity. Because somebody says, not you, but somebody would say, aha, I know exactly how to remedy this, because I know that masses increase at the moment that you go to another observer frame. So I just have to compensate for the extra mass by a gamma. That's the idea here, right? You just replace your n by a relativistic n, so therefore this should be the right rule for acceleration in special relativity. It isn't. The correct rule is gamma to the power 3. Why that is, you can also derive from that if you have a lazy Sunday afternoon and have nothing to do. But just the idea, in order to make something relativistic, you just have to replace m's by gamma m's, simply does not work. There's exactly one equation where it does work, and that's this one. So if you just restrict to this one, you're fine with the relativistic mass, otherwise forget about it. Anyway, this is the expression for the energy. We saw that if you're not moving with respect to the thing, it just gives you the famous formula E is mc squared. Suppose, are we talking about you or the water bottle? Okay, we're talking about him. This is the energy that I see that he has if he has mass m and velocity v with respect to me. Suppose that I say that he moves at the speed of light. What would this become?
Oh, you're going to divide by zeros and then
Yes.
it's going to be...
Yeah, so what do you get if you divide by 0? Infinity. So what I see, that if a mass tries to move at the speed of light, it will require an infinite amount of energy. Now you can put an enormous amount of energy into something, but not infinite amount. If you find infinite in your calculation, it means it's impossible. It takes an infinite amount of energy for chi to go at the speed of light, as seen by me. But wait, what about we just move to some other observer? I'm not looking at chi, some other guy is looking at chi, and maybe in that guy's system it takes less than an infinite amount of energy. In my frame it takes an infinite amount. Can I go to some other frame? Can I move myself in such a way that in my new frame chi's energy is not going to be infinite? The answer is no, but why?
Because the term for b is squared, so like I would think like, okay, you go in an opposite direction of the speed, and therefore the speed will increase or something. But it's squared, so it cancels.
Oh, no, yeah, that will be right if we're to just talk about switching direction.
Yeah, that's what I was thinking.
Okay, well there's a stronger argument. It's not wrong, by the way, but there's a stronger argument.
Since he's moving at c, no other observer is going to see him moving at anything other than
Thank
c.
you. We proved before that if one guy sees somebody move with c, no matter how you try to go to some other frame, every other guy will also see him with c. In other words, if some guy sees chi moving with c, in other words, in this guy's system it would take infinite energy, then any other guy will see him move with speed, c, and see him having required an infinite amount of energy. So it's not just that I cannot see him move with the speed of c, nobody can. It's a combination of two effects that we derived. This formula and the fact that if one guy sees somebody go with c, the other guy does as well. But how about photons?
Yeah, why not? They have no mass.
Sorry?
They have no mass.
That is true. So if a photon has m0 and it does go with the speed of light, you get 0 by 0. What's the answer for that?
L'Hopital.
Sorry?
L'Hopital.
L'Hopital. No, that's if you take derivatives. We're not taking derivatives here. No, I understand. At the moment that you take a limit and you find it 0 over 0, you take the derivatives of numerator and denominator, and hopefully something else will come out.
Use the equation on the upper
Yeah,
part.
you need to use the momentum.
Yeah. Use the momentum.
Yes. At the moment that a photon is moving with the speed of light, or anything that has no mass, then this term would just vanish. And you would have to use its p. Now, going back to this equation, if something moves with the speed of light, in other words, the denominator becomes 0, then you know that the outcome will be infinite. Unless the numerator itself is also 0. Because then you have 0 divided by 0. A number divided by 0, mass divided by 0 will give you infinite. 0 divided by 0, it's mathematically crappy. But it's not necessarily infinite. Right? Depending on how you take your limits, you can get a finite number out for 0 over 0. Yes?
Because the energy equation is derived from nothing, and we know that, and we can apply light to the U equation, so
Yes.
how come we are allowed to apply it to that equation?
Well, officially we're not. No, that's a good point. All of this I derived assuming that this is not 0, right? That's a point that I made before, and now I'm applying it for light anyway. So I'm not even completely. I'm not allowed to use this for things that move with the speed of light. The argument with masses moving with the speed of light, that this becomes infinite, that still holds. Okay? We're converging to the same conclusion, namely if you go with the speed of light and you have no mass, then either by looking at this, you see that something strange happens, or from the derivation you know that you were not allowed to use that in the first place. So apparently calculating energies for things that move at the speed of light requires something else. Do you know what that is? Do you know what the energy is of a photon? You have to look outside of special relativity.
Yeah, it's h times its frequency.
Exactly. So what we see here is that our formula for special relativity break down at the moment that you want to apply them to photons. So that means something else has to come in to give you the expression. It's not going to be this, and it's quantum mechanics. It's quantum mechanics that mops up that one part that special relativity cannot touch. Now the conclusion still holds. If Chi has mass, seeing him go with the speed of light requires that he has infinite energy, and he doesn't. Conclusion, things cannot go with the speed of light if it has mass. Yes?
So in the Minkowski interval, you're writing C, but if it's actually C, then it's 0, right?
What do you mean if
you actually plug in the value for C in there,
yes.
D tau would be 0.
If something is moving with the speed of light, yes.
Okay, so it's that part that's in small bracket that would be okay. Yeah, my bad. I thought you would just replace the value of C for.
Oh,
C.
I see. Yeah, yeah. It's a joke in there somewhere. Now remember that at the beginning I said that this value, this C, it's just a constant that has to be there in order to make everything dimensionally real, right? All of this I've derived. We've been constantly calling it the speed of light. It's not clear that it's the speed of light. It's just a number, and apparently it appears in all these formulas. It's up to experiment to first of all determine what the value of that number is, and secondly whether there is something in nature that actually follows this velocity. Those are two separate questions. I introduced some number in order to make the dimensions come out right. We find that apparently if you have this number somewhere inserted, that things cannot go faster than this amount. Everybody sees that thing move with the same speed. But all of this does not tell you what that number is. That's one. Separate question. Whether there is something in nature that follows this thing. Now we have found what the number is. It's 300,000 meters per second. 300,000 kilometers per second. And then it's up to experiments to determine whether there is something that actually moves with that speed. And this is the point that I made at the beginning. It's purely for historical reasons that of all the things that indeed move with this velocity, it happens to be light that was the first one that was found. So this is why we call it the speed of light. You might as well call it the speed of gravity or the speed of gluons.
Start calling it the speed of gravity from now on.
If you want, sure. Yeah, so that was my story for today. It's a very intensive special relativity course. Now, what I want you to remember from this is certainly not all these derivations. What you have to remember, mostly for our Electrodynamics, is first of all what a 4-vector is, right? How a Lorentz transform works for a 4-vector, and this particular rule. If you have two 4 vectors in this particular combination, what will come out is an invariant. That's the most important stuff.